Hi, everybody. Today we have a quiz that's on Bernoulli's equation, which is chapter 14, I believe, fluids, and is due tonight at midnight, like always. But I want to talk about it and kind of just use it as a practice question for you guys. I'm not going to put numbers in, but I will talk a little bit about how to deal with this. First thing I would like to say, is whenever you're doing Bernoulli's equation, you have only two equations to deal with. And that is something called a continuity equation, which states that the velocity at some position 1 and the cross-sectional area is equal to the velocity at some position 2 and the cross-sectional area at 2. So if this were a pipe, let's say, and it suddenly shrank down to a much smaller pipe, what you would have is the velocity of the water crossing this area would be v1a1, and the velocity of the water crossing or fluid crossing this other area. So you have this continuity equation, which allows you to say, right, v1 is a2 over a1 times v2, or v2 is a1 over a2 v1. And as long as you know the cross-sectional areas, or if you know the cross-sectional area in terms, let's say you knew that a2 was equal to 2 times a1, you could write this as a1 over 2a1, and they would cancel and you get a half. So you'd see that v2 is half of the velocity of 1. It's not too bad. The other thing that you have for Bernoulli's equation is a lot like the energy equation, except that it's, so let me write this up here, except that instead of energy, we have pressure. So we have the static pressure plus the gravitational pressure plus the kinetic pressure, if you want to call it that. And this is a lot like what we did for energy, where we had mgh, mv squared over 2, and maybe a spring, right? And you set this equal to the static pressure plus the gravitational pressure plus the kinetic pressure. And essentially, when you do that, there are a few things to remember. Number one is this can allow you to eliminate V2 or V1 if you want. The continuity equation can. 2, P is always 1 atmosphere if exposed to the air, let's say. So sometimes you won't be told in a problem, but in this particular problem that I'm going to talk about, we are exposed to the air, so you need to know that it's 1 atmosphere there. In general, depending on what you're asked for, you might need to find the static pressure, the heights, or the velocities. And usually what happens is you're either given 2 velocities in one of the cross-sectional areas, or you're given 1 velocity in 2 cross-sectional areas, or you're given the cross-sectional areas and no velocities. So anyway, the other last thing I should say is that this is occasionally written as delta P, which would be P2 minus P1. So if I move that over, that would be equal to rho G H1 minus H2 plus rho V1 squared minus V2 squared. So there's a little bit that you can do here. So let's look at the actual quiz problem. We're told that water enters a hotel through a ground floor pipe that has a cross-sectional area. So this would be your A ground, let's say, of 7.5 times 10 to the minus 5th meters squared. And then on the 4th floor, someone is going to take a shower. And that 4th floor shower head is located 16 meters above the ground floor pipe. The water exits a shower head with a cross-sectional area of 1/20th of the cross-sectional area of the ground floor. So if you called this AG, this would be 1 over 20 AG would be A at the shower head. So you know your 2 cross-sectional areas. You could also write that the height at the ground is 0. So the height at the 4th floor will be 16 meters. Therefore, we know 0, 16, And we know the cross-sectional area, 7.5 times 10 to the minus 5, and this is 1/20th of A. Okay. We're told that we can assume, or I'm sorry, the velocity at the shower head, so A2, V2, this would be your V2, is 5 meters per second. So you know that. And you can assume the static pressure at the shower head is 1 atmosphere because it's open to the air. And remember, 1 atmosphere in pascals, which is what we need to be in, is 101,325 pascals. Water has a density of 1,000 in this problem, 1,000 kilograms per meter cubed. So first of all, it tells you use the continuity equation, find the velocity of the water in the ground floor pipe. We know the velocity at the shower head. We know the area, cross-sectional area at the ground, and we know that the shower head has a cross-sectional area 1/20th of that. And by putting these things in, you should be able to get what the velocity at the ground is. This is 1/20th of A1, so basically V2 is going to be 20 times V1, or V1 is going to be 5 divided by 20, a quarter, right? So you know the velocity through the ground floor pipe, you know the velocity out of the shower head. And now what we want to know is using symbolically, no numbers. So I want you to write this Bernoulli's equation for the ground and the shower head. And then I want you to find the static pressure at the ground, meaning I want you to find P1. You know the height 1 is 0, height 2 is 16. P2 is 101,325 pascals, and you know V1 and you know V2. So you can find what the pressure should be at the ground floor pipe. Okay, that should be pretty straightforward, right? This is going to be the trickier one. So whatever your pressure that you find in part 2, I want you to assume that now we up the pressure to 4 times that. It has 4 times the static pressure. If we think about this for a second, I'm going to add a new slide. And we write it like this, okay? So we have P1 minus P2 is rho G H2 minus H1 plus rho over 2. Rho is the density of the fluid, water in this case. V2 squared minus V1 squared, okay? And if we know that this goes up, so we can actually flip this around. P2 minus P1 is equal to rho G H1 minus H2 plus rho over 2 V1 squared minus V2 squared. Now, notice that if we don't change the cross-sectional areas, which question 3 doesn't tell you to change the cross-sectional areas, the velocities aren't going to change. Okay. So let me, okay. If A doesn't change and V1's the same, then V2 will be the same. But we see that if this is now 4 times whatever we got for P2, this needs to increase. This won't increase. So what are we supposed to do here to figure out how to make this increase? What I want you to do is find the shower head velocity once we pump it up. And we know that V1 is A2 over A1 times V2. I don't want you to assume V2 is 5 meters per second. I just want you to put in for V1, I want you to put that in. So what you'll get is something that looks like this. 4 times whatever the pressure you find. Sorry, this would P1. Let me rewrite that a little bit. Well, 4 times the pressure at the ground minus the pressure at the shower head, still 1 atmosphere, is equal to rho G H shower head minus H ground. So this would be 14 or 16, I'm sorry, whatever I wrote. Did I write 16 or 14? I believe I wrote 16. So this will be 16, this will be 0, this will be 101,325, this will be whatever you find. It's going to be something like 270,000 or something. Plus rho over 2. Now this should be VS squared minus VG squared, but we don't know what VG is, and we want VS. So VG is AS over AG times VS. AS is 1/20th of AG. So this is AG over 20 divided by AG times VS, which is VS divided by 20, right? So we could rewrite this as 4 pressure at the ground that you found in part 2 minus pressure at the shower head minus rho G H shower head minus H ground is equal to rho divided by 2 VS squared, and VG is minus VS squared over 20 squared. And from this, you could actually pull this out. So you can pull this out. You get 1 minus 1 over 20 squared times VS squared and solve for VS. And you'll find it's some number. It's a little harder than parts 1 and 2. Parts 1 and 2 are fairly straightforward. Part 3 is a little bit harder, but I want you to find the velocity of the shower and just make sure you know that you can substitute in for the velocity through the ground pipe. You can turn that into something in terms of VS. In part 3, the areas will stay the same. The pressure at the ground will be 4 times what you found in question 2. Pressure in the shower will still be 101,325. Height of the shower is 16, height of the ground is 0. So you should be able to get that done. Just make sure you go through it. I just really want you to make sure that you understand how to do it. It's not hard. It's a lot like energy, like I said. So, okay, any questions on that? As always, you have till midnight tonight to get it into me. And cool. Before I start the lecture, I did want to talk a little bit about where we're at in the course, just to make sure you guys understand. So this week we are doing, well, since exam 2, we've covered chapter 7 and 8. We covered chapter 14 last week, and this week we're covering chapter 9. Chapter 9 is momentum and something called impulse. And this lab is really easy. Essentially what we're going to do is we're going to roll our IOLab against a surface and let it come back. And we're going to figure out what the force is based on that. So this lab isn't too bad. But that's everything that I'm going to test you on exam 3. Chapter 10, which we're doing next Monday, is actually a lot of stuff that we need to know for chapter 11, 12. And I just want to cover it before we really talk about 11 and 12. It's something that I'll get into a little bit today, but something you may have noticed, we haven't really talked about how to make something rotate. Turns out that's called torque, and that's not exactly the same as linear motion. Rotational motion is a bit different, and it tends to be the hardest stuff that we talk about. People have an issue with it because it's a cross product and kind of figuring it out. And so I want to do the preliminary stuff before we actually talk about problems with torque. But anyway, what that means is we have a lab on Wednesday on impulse, quick lab. Next week, we'll have a chapter 10 and we'll have a review, which means after the lab on Wednesday, I'm going to post Wednesday night, I'll post some practice exam stuff for you for this lab or for this section for Monday. It'll be the same thing. We'll have to come to campus, half of you the first half, half of you the second half. Problems will be on energy, buoyancy, and impulse, and there will probably be 4 this time. The reason why there'll be 4 is these are more plug numbers in. There's not a lot of, there's a little bit of, hey, make sure that you know the variables. And then the equations themselves are fairly easy to solve. So it won't take you as long to solve these problems. There's not a whole lot of algebra to do, stuff like that. So make sure that you start studying 7, 8, 14, which is fluids, and 9. We'll talk it through chapter 10 next week. You won't have homework on chapter 10 until we cover 11 and 12. So just make sure that you kind of, basically I want to introduce that stuff and then talk about 11 and 12 after the exam. So alrighty, and our final 3 weeks of the course, we're covering basically torque and rotation. And then chapter 15 is oscillations. And oscillations are fairly straightforward. And then oscillations and pendulums. And then the final chapter we're going to do is gravity, that first week of December, or I guess second week of December technically. Gravity will be our final chapter. And we'll have a lab on equilibrium and a lab on oscillations. But the thing is when I'm going to do something for the final, what I'm kind of leaning towards, and we can talk about it more after exam 3, what I'm kind of leaning towards is having it 50% take home and 50% in person, meaning you'll come in and you'll have like 2 questions to do in person on this torque pendulums and gravity stuff. And then you'll have like 3 at-home questions that you'll get them on Monday and you'll need to get them into me by Wednesday. Just to make it a little bit less stressful, I should say. And that we'll talk about it after the exam. So I think this exam isn't too tough. I think this exam's pretty easy, but hopefully you feel the same. Anyway, that's where we're at. We're kind of starting to head towards the home stretch, thankfully. It's been a weird semester. I think we're all kind of burned out, and then being back and jumping back and forth, it felt a little weird. I don't know, but anyway. So for today, I want to talk about momentum. And so first of all, I have a question. Is there anyone here who's ever read Newton's Principia? We talked a lot in this class about his laws, his 3 laws that everyone's kind of heard somewhere or another. But I'm just curious if anyone's actually ever read the Principia where he wrote them. And the reason why is I've read it. Of course I read it. I mean, I was a grad student in physics. Eventually you start going back to sources. It's fairly awkward, and I want to talk a little bit about that. But I also want to talk about how things kind of change. I think we all, at least at this point in history, I think we kind of feel like math, there's this like canonical math, that there's algebra and then calculus and then PDEs. And those of you who are just kind of starting in STEM, you may kind of think that there's this math is a way to do it and you just learn it. But as you start getting higher up past calculus and you start learning linear algebra and partial differential equations and ordinary differential equations and a lot of the other math, specialized math topics, you kind of start to realize that there's tools. Math is useful for some things. This type of math and this type of math is useful for other things. And in physics, it's kind of been the same way. We kind of think that F equals ma, Newton wrote it down, that's what it was. And that's not entirely true. He did have to develop some calculus to figure things out. And how he talked about acceleration was not what we think of. As far as he didn't write down F equals ma. He noticed that the way a object's speed changes, dependent if you apply a force, the object's speed changes.
Sorry, go ahead.
That's very, very different.
No. I'm just gonna add, he's just hang on.
Hi, Jennifer. So when he had to figure it out, he had to use geometry. And they basically had a way of how they figured out what the force should be and what the force was, and that difference was the net effect of the force. Very weird stuff, all on geometry. A lot of what Newton came up with, he actually was expanding on Galileo's work. So Galileo understood or had come up with these ideas of centripetal forces, and Newton expanded it. Newton's kind of way of doing things was he would explain it by using examples. And he would give you every example in the book, everything he could think of. He would try to think of 50 different examples of a force, for instance. But the big key here is that nowadays we say Newton's first law, you guys know as an object at rest stays at rest, an object in motion stays in motion unless acted upon by a force. And then the second law we say is F equals ma. And the third law is that forces are third law pairs, that things act on each other. So this is kind of the A equals 0 case or constant velocity. Third law pairs means that F is actually F external is equal to the mass times A. But none of that is really what Newton said. Newton actually talked about something far simpler. And we've kind of taken a very long road to get to something really simple that explains a lot of real life stuff. What we're going to learn today is simple, and it explains things remarkably well. Amazingly, it's pretty accurate on a human level, and that makes it beautiful, because if it's simple and it gives you good results, A+, right? If we didn't have to do integrals, we could just do algebra, we would all be mostly happy, right? Well, what Newton realized is that there's something called momentum, and it's actually the momentum that changes, and that there's a conservation law with momentum. In fact, he fixed some of the earlier stuff that people didn't realize what was completely happening. And we'll learn a little bit about that in gravity, where Kepler mathematically figured out that the planets sweep out equal areas in equal time. Newton said, yeah, that's conservation of angular momentum. He figured that out in a very simple way. But we're basically going to simplify everything down to something called momentum. And there's a lot today that we need to talk about with momentum. There's a lot of background stuff. The actual use is easy. Understanding it and understanding the subtleties of it can be a little daunting. It may take you a while to completely understand. It's kind of like you go to a friend's house and you start playing a board game, and they explain the rules. So you're going along and you're playing the game, but you don't get the subtleties of it. You don't understand why certain things are going on. I'm going to try to tell you why the certain things that are going on in the background. And I'm going to explain the easy way of, hey, here's the equation, here's how you apply it, here's how you get the right answer that you want. But to start off, we really do need to understand what, and do I really want to go there? I want to jump down a little bit, and I'm going to come back here, because it made sense this morning. And then as I've thought about it, I want to actually, as I start talking, I want to go a little bit different direction. So let's restate Newton's first and second law. And actually, this isn't the full story. What Newton's second law, we said, was a definition of mass, which is how resistant something is to having its velocity change. Acceleration, which is the change in the velocity. And external forces. Newton's third law says that internal forces all cancel. So we never have to worry about external forces. But we've already learned that the acceleration is the derivative with respect to time of the velocity. And so we can rewrite this, F meaning external forces, as dv dt. Further, we can actually move this inside our derivative. And so when we do that, this actually becomes what is the big secret here. This is what Newton actually said in his second law, was that when a force is applied to an object, its momentum changes. And momentum is simply mass times velocity. It's a quantity. It's the secret of the universe, as you'll see today. There are so many problems that you can simply sit down and say momentum is conserved, and therefore I can look at the change of momentum. I know it all equals 0 when I sum it together because it's conserved, and we'll go from there. How an object's momentum changes with time is a force. So a force changes something called momentum. And this is linear momentum. We're actually going to talk about angular momentum after exam 3. But linear momentum, if it changes with time, it's because of a force. If there's no force, then the linear momentum is conserved. And what that means is the initial momentum and the final momentum will be equal. We'll eventually get to that and talk about that. It doesn't mean that there's no change in the system. A ballerina or a figure skater or a diver who can cause themselves to rotate can actually change their linear or angular momentum of different parts of their body, but their total momentum doesn't change. However, before we get there, we do have to deal with this little pesky problem. We started this whole class, I don't know if you remember way back when, we started talking about mass. And what is mass? What the heck is mass? And we've kind of said this whole time that mass can be constant. In this chapter, we're going to talk about something called the rocket equation, which is what happens when your mass changes. We're going to kind of talk a little bit about changing masses, but a few things to know is that we're going to assume uniform densities, which means that the density, not the momentum, but the density mass over volume is equal to any small mass over any small volume. But as far as what mass actually is and what momentum is, it's a little bit, you've got to make sure that you don't equate the two. Much like a mass has energy, a mass that's moving has momentum. And you know that, right? If you get hit by something that's moving, it hurts, right? Someone, is driving a car and bumps into you, it hurts. Momentum's a real thing. It's weird. If we look at these units, and this is kind of funny, the units are kilogram meters per second. And we'll talk more about what that is. There is no actual name for the units of momentum. We don't call them newtons, we don't call them joules, we don't call them watts. I read an article on Reddit where someone was calling them moms. There is no unit of momentum. The momentum of an object is just, it's momentum. It is what it is. But before we get into all this, we need to come back to the secret of motion. And when we talk about a system of particles and we say F is equal to the change in momentum, what we really mean is that, and I shouldn't be drawing that as a row, I'm sorry. What we really mean by the momentum is we mean the center of mass times volume, or times velocity. What does center of mass mean? Well, one of Newton's really, really major contributions was he understood that an object's center of mass is the point where if all the mass were concentrated at that point, the physics would stay the same, which means you can simplify any system of particles, objects, to a system where all of its mass is at the center mass. And what do I mean? Imagine I have a whole bunch of masses and they're all traveling at some constant velocity together that way. This is exactly the same as if all of these, if each of these were one mass, right? It's as if there's a 5 mass particle at the center, at the mathematical center of those objects traveling at that same velocity. That greatly simplifies a lot of problems. Essentially, you could have a train that you treat as a particle at the center mass of a train. You can have a moon rotating around the Earth that you treat as a particle with no width, no height, no length, no dimensions, just it's a particle where all of its mass is at the center. And Newton proved that for a lot of things. It's kind of amazing that he was able to prove that. We're going to talk about that. I have given you some homework problems with center of mass problems. In most problems, we don't need to worry about it so much, but if those of you going into engineering, those of you going on in physics, you might even need this in chemistry. You need to be able to understand where the center of mass of an extended object is. And we're going to use the simplest objects, uniform objects that have symmetry. And I'll talk about what that is. But, okay, so as a first easy thing to understand, if we add up all of the masses, so if we sum the masses and we multiply by the coordinate of the center of mass, we should get each individual mass and its location. This will make more sense in a minute, but in one dimension, the total sum of all the masses times the position of the center of mass is equal to each individual mass times its position summed together. So it's the sum of all of the addition. Now you can see from this, we have to choose an origin. We actually technically should rewrite this as x minus x naught, minus x naught, minus x naught, right? Because we have to have an origin. We, as physicists, we're kind of lazy. We leave off that minus x naught and just imply that you're measuring from some origin. So how does this work in real life? So let me explain it like this, and this will be the simplest example that I can come up with. Imagine you have 2 blocks and they're connected from their center to their center. These are each 2 kilograms. And you have connected from center to center a distance of 3 meters, okay? And we want to know if we wanted to treat this as a single point mass with a mass of 4 kilograms, where would that single summed mass be, okay? Obviously, your intuition probably goes, well, it's going to be right in the halfway. They're equal masses. Yeah, but can we mathematically prove that without relying on intuition? And the answer is yes. Sum of the masses times the x coordinate of the center of mass is equal to mass 1 times x1 plus mass 2 x2, or this. The sum of each mass times its displacement, well, not displacements, its position, divided by the sum of the masses is the position of the center of mass. The first thing that we have to remember is, where is our x naught? I'm going to draw it here. So x naught is 0, which is x1. And therefore, x2 is 3. And I can write this as 2 times 0 plus 2 times 3 over 2 plus 2. What I get is 2 times 0 is 0. I get 6 divided by 4, or 1.5 meters. Okay? It's right in the midpoint. Cool. You might be saying, yeah, that's dumb. I could have done that with intuition. Why would I need to do it mathematically? What happens when we don't have a couple of nice, symmetrical masses? And I'll talk what symmetry means soon. But what if instead now we have the same thing, but this one, instead of being 2 kilograms, is 200 kilograms. So now we have 200 and we have 200. And so we have 600 over 202. And that, you might be saying, well, that's not much of a difference. But 600 divided by 202 is 2.97 meters. So when they're equal, it's at the center point. When this one's 100 times bigger, it's almost right on the edge of the center of the second block. This is a lot what happens with the center of our solar system with the sun. Our sun is massive. So you would think that it is the center of our solar system, but it turns out it's not. And that's because while most of the planets are very small, microscopic compared to the sun, Jupiter is actually quite large. And so Jupiter offsets that center. The center of the solar system is not quite lined up to the center of the sun. But the big takeaway here is that in one dimension, we can write that the position of our center of mass is simply each individual mass times its position divided by the sum of all the masses. Quite easy, quite nice. That works for particles. We're going to talk about objects in a minute. So here, I did something a little bit different in this one. What if instead of putting my 0 at the center of this one, I instead put it here. So this is 0 and this is now at -3. Okay, I can do that. I can set my 0 wherever I want. When I do that, what I find is my center of mass is -6 over 202. This is going to be like minus, what did we get, 297? So this is going to be like minus 0.03 meters, meaning it's right here at minus 0.03 meters. It's going to give us the same answer relative to where we chose our origin. Just make sure you understand that. Okay, if we have multiple dimensions, nothing changes. You just handle X, Y, and Z separately and figure it out. We're going to do a bunch of these, okay? So imagine we have a square of 4 equal masses. Let me do it 2 ways. So what if I did this? This one is at 1, 1. I don't know why I did a fraction. This one's at 1, -1. This one's at -1, -1, and this one's at -1, 1. If we wanted to find the center of mass of these 4, we know it's right in the center. Let's say they're all a m mass. So it'd be 4m, and let's say m is also 1 kilogram. I don't care. To find it in the x and find it in the y, x of the center of mass and y center of mass are m1 x1 plus m2 x2 plus m3 x3 plus m4 x4 divided by the sum of all the masses. Same with the y. And it gets really tedious, but you can do it. Now, m1 is 1, x1 is 1. Let's call this 1, 2, 3, and 4. m2 is 1, x2 is 1, m3 is 1, x3 is -1, and m4 is 1, and x4 is -1. 1 plus 1 minus 1 minus 1 divided by 4 is 0. m1 y1 is 1, m2, y2 is -1, this one, 1, 1, 1, -1. And again, over 4, we get 0. So we know the center of mass of these is 0, 0. We could actually move our origin to say on this mass, and then we could do some other stuff if we wanted to. Not a big deal. You simply assign an origin, figure out what the x coordinates are for all the masses, what their masses are, figure out what the y coordinates are, and solve it. Now, here's one that your engine may not be great on. Imagine we have a right triangle. This is 2 kilograms, just to make it nice. Now I have a right triangle. It means a triangle with a 90-degree angle. I'm going to say that this is 2 and this length is 1. So maybe I'll just write them inside. 2 and 1. I don't really care what this is. Therefore, this mass is located at 1, 2. This mass is located at 1, 0. And this mass is located at 0, 0, assuming my origin is right here. Okay. And I want to know where the center of mass of this thing is. It's not obvious. You might think, oh, well, it should be like here somewhere. Although it definitely isn't obvious. So in this case, I can make this triangle act like a single particle of mass 2 plus 2 plus 2 of 6, but I don't know exactly where that particle would rest. How do I do it? XCOM, YCOM, M1, X1, plus M2, X2, plus M3, X3 over the sum of the masses. M1, Y1, M2, Y2, M3, Y3 over the sum of the masses. Let's say this is 1, I get 2 times 0. The x coordinate is 0. Say this one is 2, the x coordinate is 1. Let's say this one is 2, the x coordinate is still 1. So this is 2 plus 2, this one's 0. So that is 4 over 2 plus 2 plus 2. Sum of the masses is 6. What about this one? 1, 0, I'm sorry, 2, 0, 2, 0, and 2 times 2, which is 4 over 6, or 0.66 meters and 0.66 meters, which means this thing is at 0.66 and 0.66, strangely enough. That's all you have to do to find the center mass. You just use these equations over and over again in X and Y. It's not hard at all. In fact, there's ways to make it much easier. Imagine that you have a sphere. So we have this sphere and it's uniform. So it's like that rubber that we used for the buoyancy lab last week. By the way, I forgot to put the buoyancy lab up. Buoyancy lab's on, it's due on the 14th midnight, which is a week from Sunday, or a week from yesterday. Okay, so we have a sphere of uniform density. We intuitively, as a human, kind of understand that the center of mass is at the center of the sphere. But can we prove it? And this becomes harder than you might think with what we know right now. Okay, but it's actually super easy to prove. So instead of having multiple objects, now we have one big extended object. And we can think of any extended object, for instance, a sphere, as being made up of a bunch of little DMs, okay? Little infinitesimal pieces of mass, right? And if it's uniform, that means rho is constant, where its rho is the density over the volume, or if it's a linear object, like a stick, that we assume doesn't have any significant width or height, we could also say that the linear density is the mass over the length. There's some things that we'll talk about at some point with that. But in this case, we can say that a rod has a linear density. And usually I think they use sigma or lambda, for linear, where lambda is mass divided by length. And sigma is mass divided by area for a two-dimensional object that has no actual volume. So they're all kind of used interchangeably. We'll talk about that when we get there. But let's now imagine that we have a rod, okay? So we have this rod, and we know that this rod has a uniform density. So we know that it's dm over length, mass over length is true. The actual way to find the center of mass of this rod, so let's say this rod is length L. The actual way is to take the sum of the masses times the x is equal to the sum of the x's times dm. That might look weird to you. It may look weird to you, and that's okay. But rewriting this, we get the sum of the x's times dm over the sum of the masses. We know that the sum of the masses of this whole rod is m. This rod has a mass m. What we're left with on top, however, is the sum of the distances times each little infinitesimal piece of mass. We assume that we can take those infinitesimal pieces of masses so small that this effectively becomes an infinite sum. An infinite sum is an integral from 0 to L. And in this case, it's 0 to L x dm. Now, we need the mass in terms of length. Well, one thing we can do, we're going to divide that by mass. One thing we can do is we can multiply by dx over dx, okay? What I should say, and I should have said it here, this is really dx is m over L if it's uniform. So what we get is that x of the center of mass is the integral from 0 to L x dx dm over dx over m. Now dm over dx is rho. We can take the rho out, but since rho is m over L, what we get is this becomes rho, which becomes m over L divided by m times the integral from 0 to L x dx. What does this become? X center mass is the integral from 0 to L x dx times 1 over L. This integral is x squared over 2. So what do we get? We get L squared over 2 divided by L, which is L to the half. This is from 0 to L, right? And what that means is, after doing all of that really hard stuff, is that if we have a rod length L, right here at the center, at L to the half, is our center of mass. We proved it with an integral. The integral is x of the center of mass is 0 to L x dm over the sum of the masses. That's what it is, oddly enough. And that gives us length to the half. If you think about this, this integral is some distance times some mass divided by mass gives us a distance, so it works out. So we know that the center mass of a uniform rod, could be a pencil, could be a long stick, could be a ruler, is at the halfway point. We've proven that with calculus, believe it or not, which is cool. We're not going to worry about non-symmetric objects, and what that means is, like, say, a base or a cone is non-symmetric. I mean, it is symmetric about the central axis. We're not going to worry about that. We're going to worry about spheres this, rods, things like that. But if you did have an oddly shaped object, what you would do is, let's say we have some weird object that's sitting here at the origin, right? In order to find the center of mass, what you would have to do is you would have to figure out what the R vectors are to each little dm, and you would end up getting this. This you would turn into your R center of mass in terms of the volume. So R center of mass, if this is a vector, is 1 over V R dV, and you can do that integral. We're not doing that integral. Those integrals are horrible. With symmetry, what we can do is we can actually eliminate the integrals. So let's talk about that. For a sphere, uniform density sphere, we set it right at the origin. Okay, so we're going to set our sphere right at the origin. Now, when we try to do this integral, 1 over R all the way around the volume, we should note that if we go out some R to some dm, and then we go out some R to some other dm, they're going to cancel. This R is going to be negative, this one's going to be positive, and we're going to get a cancellation in the integral. In fact, every vector is going to cancel pairwise. What that simply means is, one points this way, one points that way, they cancel. One points up, one points down, they cancel. All of them cancel. So if it's at the origin, this integral is 0. And we know that the center of mass of a sphere is at the center. That's really useful. When we do gravity, we're going to come back to this and actually talk about the fact that only the mass inside your radius contributes to gravity, but we'll get there. But just understand that if I start at the origin and I draw vector R1 is -1 times dm, and I draw some vector R2 that is 1 times dm, whatever dm happens to be, those two will cancel out. And you can find an infinite number of pairs that just all cancel. Symmetry is very, very useful in physics because it allows us to actually sometimes compute things that we otherwise would have a very difficult time computing. Or at least in the old days we would. Computers now can deal with things that we, even 20 years ago, would have to be a very, very good mathematician. If you've done your solids of revolution, you understand that. Some solids are very hard to do. But we're going to deal with symmetry in this class. So what that means is a sphere, the center of mass is at the center. A disk, if it's uniform, center of mass is at the center of the disk. A rod, center of mass is at the halfway point, et cetera, et cetera. But let's talk a little bit about one of the other symmetry uses, like parasymmetry in a weird way. Imagine I give you, and I did in the homework, I give you a pyramid, okay? So it's an object that has 5 equal masses in the shape of a pyramid, okay? And I want to know where the center of mass of this pyramid is, okay? Now, I know I've got this slightly weird, but let's say that I draw it something like this. And then this is in the Z range, right? And this is right in the center of the pyramid, okay? So the Y is at, let's say, this one is at 0, 0, this one's at 4, 0, this one's at 2, 0, and this one's at 2, 0. And I'm only talking about X and Z here. I'm not dealing with the Y's right now. So we know that in the Y and X direction, if this was along X, let's say, so let's say this one was at -2 and this one was at +2y, and then this one was at 0. Let me actually add the z's. I didn't want to get too complicated, but I guess I ought to add the Z. These are all at 0. Hopefully that makes sense to everybody. In the Z direction. And we're in 3 dimensions, okay? So we have these 4 points, and we want to know where the center mass of the pyramid is. Now, we could write the X center mass and the Y center mass equation that we did before, M1, X1, blah, 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 blah. Or we could note that we already know if this is a square, we know it's at the halfway point, at the middle center of the square by symmetry. It has to be, because these things cancel parallels. So we know that X and Y are 2 and 0. 2 in the X and 0 in the Y. You can prove that to yourself, but all we're left with is Z. And so Z, we have M1, Z1, M2, Z2, M3, Z3, M4, Z4, M5, Z5. It gets tedious, I know. If all these masses are 1 kilogram, we know that Z1 is 0, Z2 is 0, Z3 is 0, Z4 is 0. They're all at 0. Z5 would be 1 times 4 over the sum of the masses. They're 5 kilograms. This is 4/5 in the Z hat direction, 0.8, which means that our pyramid that we have, our cool pyramid, can be treated as a point particle that's 4/5 of the way up. Why does that seem backwards? That seems like I've flipped something there. And that's bugging me. Y would be 0, X would be 2. But then I feel like it should be closer to the bottom. I guess not. 4/5 of the way up. Weird. Strangely. Yeah. Hopefully I didn't mess. I don't think I messed anything up. It just feels like it should be like a 1/5. I feel like I've got something slightly wrong. But all right. Z position is 4. It's over. It's a 1/5 of 4. Oh no, I'm totally fine. I drew it wrong. That's what I did. I was thinking it was 4. It's 4/5, so it's less than 1. It's, somewhere around here is where the center of mass is. It's only 4/5, so 0.8. This one's at 4 meters. This one's center of mass is at 0.8 meters. Okay, so here's another cool fact. And this fact I'm going to try to do a little bit better job explaining. So the total center mass of an object is equal to the center mass of each object times their mass. So what I mean is, imagine you have, I don't know, a box with a sphere on it, and it's on top of a bunch of rods, and they're all glued together. And you want to find where the center mass of the whole object is. Well, the total center mass is, so Cm is equal to mass 1 times X center of mass for mass 1 plus mass 2, X center of mass for mass 2 plus blah, 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 over the sum of their masses. You might be going, well, imagine this. Let's say we have a disk, okay, centered on the origin. And this disk has a mass m. And we know that the center mass of this guy is at 0, 0, okay? So we know that m times x is equal to, divided by m, is equal to x center mass, and we know m times y over m is equal to y center mass. But now, what if we remove this little m, okay? So we remove this little m, whose center mass in the x whose X center mass and Y center mass is now, if this thing has a radius of 1, its center mass is at 1/2. Okay, this point right here is at 1/2 and it's at 0. Y doesn't help us because these originally were 0 and 0, but what about X? So M times X center mass, right, has to be equal to M minus M times, let's just call it X center mass prime, plus, and I really should make these look a little bit better. I'm going to put these on it for the big M, and this is little m. So big M minus little m, and little m times its center mass, which is 1/2. Now, let's say big M was, I don't know, 30 kilograms, and little m was 5 kilograms, okay? I know this is 0. So what that tells me is now m minus m times x COM is equal to minus little m to the 1/2. This I know is 30 minus 5. This I know is minus 5 times 1/2. So what I would get is that X center mass prime is minus 2.5 divided by 25, or 1/10, right? Minus 0.1, which tells me what? It tells me that when I take this away, the new center mass is at minus 0.1 meters. What this is telling me is that the sum of each mass times each center mass is equal to the individual masses times their center of mass. This becomes very, very, very important. I don't want to do that. Very important for things that you cannot calculate, right? So basically, if I had some weird object, right, like a, I don't know, a rock in space, right? So I had some weird rock. I could actually figure out its center of mass by making it into smaller ones that maybe I could add together. So basically, the total center of mass in X, Y, and Z, okay, their total center mass is equal to each mass times X center mass or Y or whatever, plus the next one, plus the next one, over the total mass. And that is, it may not seem very helpful right now. That is hugely helpful when you may not be able to calculate a center of mass. And so just to be clear, let me state it another way. If I needed to find the center of mass of a moon-shaped object, right, I could actually figure out, if I filled this in, if this was uniform, I could figure out what the total center of mass was, remove that, and it would give me, so let's do it this way, okay? I want to find the center of mass of A, and this whole thing would be C, right? This whole thing would be C. So the center of mass of C is equal to MA times the center of mass of A plus MB, the center of mass of B, over MA plus MB. And therefore, if I want the center mass of A by itself, I would get MA plus MB times the center mass is equal to MA center mass of A plus MB center mass of B. And rearranging a little bit, sorry, I want the center mass of A, is equal to MA plus MB times the center of mass of A plus B minus MB times the center of mass of B, all divided by mass A. That's nice. We can find the center of mass of weird objects by making them whole and then taking things away, let's say. It's really weird. Your book does a very good job of showing this with this particular example. It's a neat little mathematical trick. And let me go to it. This is one of those examples in the book that I really actually like. And I don't like a lot of examples in the book. I think some of them were too hard, some of them were too easy. But this one, just go ahead and take your time and read. Read through it after lecture if you haven't already. It's right here. So it's right after checkpoint 1. This is actually figure 9.4. If you know this object's mass and center of mass, which is 0 if you set it at the origin, and then you remove a disk which has a center mass in its own origin and some smaller mass, you can find the center of mass of this, because this mass times the center of mass, this mass times the center mass minus this mass times the center mass is this mass times its center of mass. Weird, huh? Strange, but it works. It's really nice that it works. And you might need it. This is another one of those like, whatchamacallit, the guy that, the Eureka thing last time. Just weird. So anyway, let's pause for a quick second and just say this. So center mass is, if it's X, it's M1 X1 plus M2 X2, etc., over the sum of M. So MI, let's say, from I to wherever the final one is. And you can do that for Y, you can do it for Z. That's all you have to do to find the center of mass. You can use symmetry sometimes. You can choose your 0 sometimes to help you. And then mass total times center of mass total is equal to mass A times center of mass of A plus mass B times center of mass B, etc. That's all you need to know from this part. But X can be a Y, same for Y, same for Z. Okay. You don't need to know the integral one. It was just a proof of, for a uniform rod, the length in the middle is, the center of mass is in the middle. Okay, so that's it for that. And we're going to talk about some homework with it at the end of this. We've talked about this already, but just to be clear, Newton's first law says that an external force is equal to the time rate of change of the momentum. If no force, conservation of momentum. Now, what that means is if F equals 0, then mv final minus mv initial is 0, or mv final is equal to mv initial. However, this is a bad way to write it. You really want to think P initial of the system is equal to P final of the system. Because the momentum can still change, it just has to change in such a way that the total changes 0. And we'll talk about examples of that. Okay. So P is a vector. It has components, so we can talk about the momentum in the X, the momentum in the Y, and the momentum in the Z. Just like we talk about the velocity in the X, the velocity in the Y, velocity in the Z. It has the same vector quantities as, or vector quantities as velocity. In fact, it's because of the velocity. And it can have it in all different directions at the same time. It could be, doing some weird circular thing where it's got some momentum in the X and Y and Z. Nice thing is we can handle all of them independently. They are all independent of each other. And then finally, momentum is kilogram meters per second, MB. It has no name. So we never talk about some weird unit of momentum. As I said, Newton's first law told us that if a body's at rest, it stays at rest unless acted upon by a force. A better way to say that, now that we've gone through several months of physics, is the momentum does not change unless there's an external force. The total net momentum of an object cannot change unless there's an external force. Hey, dude, you all right? Okay, so no external force, conservation of momentum for the system. And I cannot argue that enough. I'm gonna talk about an example in a second. But so imagine you are one of these lucky people that get to go up into space, and they start letting you go outside the space station. So you have on your astronaut suit, you have your astronaut suit on, and you have a tool, a wrench or something, and all of a sudden you find yourself floating away from the space station capsule that you want to get back to. You find yourself floating slowly off into the darkness, okay? Now, let's say your velocity is, I don't know, 0.5 meters per second, and you weigh 60 kilograms, right? And you begin to panic. You're going to float off into space and die, okay? Your total momentum is your mass times your velocity, so mass of you times your velocity, plus the mass of the wrench times the initial velocity. However, you get a bright idea, and you throw that wrench behind you as hard as you can. So you throw the wrench, and the wrench goes sailing away at 10 meters per second. And let's say the wrench has 1 kilogram mass, okay? So now you're at 59 kilograms, going the other way, okay? So this is 60, actually, let me come back to that. So this should really be mass of you plus mass of the wrench times the initial, and that is 60 times 0.5 or 30 kilogram meters per second. That is your initial total momentum. After you throw the wrench, we don't know how fast you're going to be going. We're assuming it's going to be that way. So after that, your weight, which is now 59, times your velocity final, plus the mass of the wrench times the velocity final of the wrench. This was 10, this was 1. This is your final total momentum. It has to equal the initial. There's no outside forces acting it. And we'll go through this more, but so we get 30. We want to find what your velocity is. So 30 minus 10 is 20. So 30 minus mass of the wrench, the final of the wrench, is equal to 20. 30 minus 10, 59 times V. So 59 times V. V is equal to 20 divided by 59, which is a little bit less than a third. Let's call it a third of a meter per second. Well, unfortunately, that means that you are going to drift out into space forever, because your velocity is still positive. Now let's change this. What if it was a, I don't know, a 10 kilogram wrench and 10 meters per second? So now this is 100, and we get minus 70. 30 minus 70, I mean 30 minus 100 is minus 70. So now what we get is and this becomes, unfortunately, this becomes 50 now that we're, so this is 50, 50. So now we get that B is minus 70 over 50, which is whatever that happens to be. 70 divided by 50 is minus 1.4 meters per second, which means if that wrench weighed 10 kilograms, your velocity is now 1.4 meters per second to the left. Now let's look at what happened, okay? So, and this is really important. Prior to anything going on, your initial momentum was your mass times the velocity plus the mass of the wrench times its velocity, but these were the same initial velocity. After, okay, after P final is equal to P initial, you still have the same momentum. We'll prove that in a second. But your mass times your final velocity plus the mass of the wrench, final velocity of the wrench, have to equal your same initial velocity. So are we somehow violating something? Amazingly, here's where center of mass comes in, okay? The center of mass is moving with a velocity of 0.5 meters per second, okay? If we were to slowly take a snapshot of the wrench and of you, and as you move further away, what we would see is that the center of mass still moves with the same velocity of 0.5. Amazingly, the center of mass's momentum never changes. It has the mass of you plus the mass of the wrench and a velocity of 0.5. However, your change of momentum and the wrench's change of momentum are exactly equal, okay? These two things have to equal these, which means mu v initial minus v final has to equal m of the wrench v final minus v initial. In effect, your change of momentum is the negative of the wrench's change of momentum. Why? There's no external force. So what we have to do is we have to write P initial is equal to P final if F is 0. And then we write M1 V1 plus M2 V2 plus is equal to M1, let's call it V initial, M1 V1 final plus M2 V2 final plus, and this is V1 final or V1 V2 initial. So basically we add up all the initial momentum for each part of a system and we add up all the final momentum and they have to be equal. It turns out that this is actually the secret of all motion. And there's a reason why, and I'll talk about that in a minute, but if you want a little bit to go through this and make sure that you've got it. 75 kilogram astronaut at rest holds a 2 kilogram tool in their hand. The astronaut throws the tool away from himself in the negative x direction. So they start here, he throws it in the negative with a constant speed of 8 meters per second. So how much momentum is this thing carrying in this direction? 2 times 8, 16 kilogram meter per second. Therefore, the astronaut has 16 kilogram meter per second of momentum going the other way. If you want the velocity, you take that 16 and you divide it by their mass, 75. Ends up being 0.21, headed to the right. Now, we have actually ignored something really important here. And that is, we need both objects to be in the same rest frame, okay? Meaning their velocities relative to each other are the same as what they are. We can't have some weird velocity change happen. Another way of saying that is that we can choose a frame that doesn't have an external force acting, is what I'm really trying to say. One of those frames cannot be accelerating with respect to the other one because then you would have external force. If you chose a big enough frame of reference where there could not possibly be any external forces, then all momentum would in effect, be paired up. Any momentum, me moving my hand like this, would have to result in a loss of momentum or momentum in the opposite direction. I shouldn't say loss. It would have to result in a counter change of momentum. Me moving at all would have to result in a counter change of momentum somewhere else in the rest frame. Well, if we took the entire known universe to be closed, meaning it's all at rest, there are no external forces, then all objects that change their momentum do so by causing another object, or a change of momentum of one object causes some other object to change momentum. That's really weird to start thinking about when you start thinking about motion, that the only way you're able to change your momentum is if something else changes it along with you in the opposite way. Strangely, third law of pairs, equal and opposite forces. In an external or in a big enough rest frame that there are no external forces, all momentum is conserved. Momentum is conserved universal, just like energy is conserved. Just like we can say the energy initially and the energy final, if there are no external forces, are conserved. We can also say that if there is no external forces, there's no change in momentum. There's no net loss or gain of momentum would be a better way to say it, which means everything that gains momentum is because something else changes momentum opposite, just like the wrench in the face the astronaut is faced. If you're moving, it's because something else is moving opposite. Something else has a negative momentum of yours. Quite weird to start thinking about, but it works. In terms of momentum, it works. And it's really simple. And we'll talk about an even simpler thing. But you might be thinking, oh, well, that's easy. Turns out there's something even easier, something much more universal for researchers and humans. And that's an idea of something called an impulse. We talked about work, and work, a force dotted with a distance or a displacement, meaning a force that causes an object to move in the same direction as the force, increases the kinetic energy of an object. Basically, work adds energy or subtracts energy depending on whether the force is parallel or anti-parallel to the object. But what if we applied that force for a time instead of a distance? What are our units if that happens? So imagine you have a force and you're going to apply it for some time, some amount of seconds. So I'm going to push on a block to move it across the floor. I'm going to push with 600 newtons of force for 4 seconds. What do I do to that object? Well, newtons per second are kilograms, meters per second squared times seconds, or kilogram meters per second. A force applied for a certain amount of time causes a change in momentum. When you have an external force acting on a system, it changes the momentum of that system. In fact, it's the only way that you can change the total momentum. And you might be thinking, this is really super useful for analyzing motion of all kinds. We're going to talk about car crashes. We're going to talk about baseball, American baseball. I don't know if there's anything other kind of baseball, but baseball. And you can extrapolate it to everything. It's actually quite amazing. There are some shortcomings that I will talk about, but for now, the impulse is a change in momentum, okay? So an external force applied for some time is a change in momentum. We have to consider that force to be a constant average force, unfortunately. So when we're talking about a force, it will be a constant average force. Why? Because we don't want to integrate the force times time to get a change of momentum. It would be hard if you had a non-constant force. You would have to somehow understand how the force acts with time so that you could integrate it over a certain time. And yeah, it's not fun. So we also need to understand that when we apply an impulse, momentum can be conserved by different parts of the system. The other thing is that if we choose the right system, there's no internal forces. I already talked about that. We'll talk about that a little bit more when we talk about collisions, but let's talk about impulse. Okay, so impulse. If I apply an average force for some time, I get a change of P, which is a M V final, M V initial. Now, one thing I need to understand with this, signs. Your signs have to be signs. Your signs have to be consistent. F is only an average. It's an average value of the force. So if we had some change of momentum that we could calculate and divide by some time, we could calculate the average force that caused that change of momentum. What do I mean by a change in momentum? Imagine a pitcher throws a baseball toward a batter, okay? So there's someone standing with a bat in baseball, and the baseball has some mass, and it's got some initial velocity. If I assume that X goes this way positive, that initial velocity has to be negative, right? After it's hit, the ball's going to travel here, get hit, and head back the other way. After it's hit, V final will be positive. Technically, what we want is the velocity right before the bat hits it and right after it leaves the bat. Because what's going to happen is the ball's going to be here, and the bat's going to swing back through. The ball's going to make contact, and then the ball's going to change direction and head back the other way as you swing. Okay. So as you swing, it's going to be in contact for some small delta t, and we're going to figure out the average force based on actual numbers from baseball. Now, I don't know why, I'm sure I could find it on the internet, but impulse is usually given J. Impulse is F times T, same units as momentum, Newton seconds. Usually you don't call momentum Newton seconds, but you do call impulse Newton seconds. And I think that's to differentiate that we're talking about a force being applied for time, Newton seconds. So imagine in our example, we have our 2 kilogram mass baseball. It's initially thrown with a velocity of negative 44 meters per second. After contact, V final is 39 meters per second. And we know the delta t, the time it was in contact, was 0.8 seconds. Okay. So what we can do is we can write F average t is M V final minus M V initial, which is F average, which is what we want, is M V final minus V initial over T. Now M was 2, V final was 39, V initial was a negative 44, so this is plus 44, and the time was 0.8. So I have 70, 83, I have 166 divided by 0.8 is my average force. 166 divided by 0.8. 166 divided by 0.8 is 207 newtons, 207.5 newtons. Okay, so what that means is it took 207.5 newtons being applied for a duration of almost a second to change completely, almost completely, the ball's momentum. So F delta T is equal to the change in momentum, MV final minus MV initial. The only thing you need to worry about is you need to know that one of those directions was negative. It changed direction. So if you had messed up and you put this as positive, you would obviously get a negative answer, and that's not correct. Okay. But we find 207.5 force. We don't know if that force varied during that 0.8 seconds. It probably did, but we know the average force was 207.5. Again, if you think about this, it's really hard to get a force gauge on a baseball or a bat, right? You couldn't really make a bat with a force gauge in it. However, you can take a high-speed camera, you can get the velocity of the ball right as it makes contact with the bat. You can time how long the bat is in contact with the ball, and you can get the final velocity as it leaves the bat. And from that, you can calculate the average force during the impulse or contact. That's important. It's a little for baseball. It's important for other things, for things that we care about, for things that we worry about, the safety of humans, you know, or other things. Let's talk about this a little bit more. Now, you may not know what a bunt is, but in a bunt, when you're playing in baseball, instead of swinging, you'll hold the bat steady and kind of have the ball bounce off it. What that means is the time of contact is really very much reduced. So if it were reduced to 0.3 seconds, what is the final velocity? So remember, we have, assuming that F average is the same, T is MV final minus MV initial. Well, MV final is F average T plus MV initial. If we divide through by M, assuming the same 207.5 and 0.3 now, plus, what was it? A 3 kilogram or 2 kilogram baseball. 2, V initial was still the same, minus 44, and divided by 2. So you can see all this here. We just rearranged it to find V final. Doing that, you get a minus 12.9. Now, physically, that doesn't make sense. That would mean it went through the baseball bat. Maybe it did, maybe it broke it in this case. But I could figure out a time, maybe 0.04. 0.4 might be 0.4 times 207.5. 0.4 times 207.5 is 83. So maybe 0.5, it would actually go forward a little bit if it was in contact for half of a second. All right. Now, any of you that have played, you can actually decide, Rudy, if left to right. You just need to know that if the velocity is changing directions, one of them better have a negative sign.
Yes, can we go back to the previous slide just to see the wording of the problem?
So, a 2 kilogram baseball is pitched at the batter at 44 meters per second. The batter hits a line drive right back at the pitcher with a velocity of 39. So you need to know that those two are in
Opposite directions.
Yeah.
But how do we know which one gets the negative?
It doesn't matter. You can choose whichever direction you want to be the negative. You just have to know that the momentum completely changed. It completely went in the opposite direction.
Yes.
All right. So for those of you who have ever played golf, maybe in, I don't know if they tell you to do this in soccer. I know they tell you this in baseball. They'll tell you to follow through. So in golf, they want you to follow through. Don't shorten up your swing. The reason for that is you want as long of a time of force being applied. You want the impulse to last as long as possible for that golf ball or baseball to travel as far as possible. So what if we extended the time to 1.2 instead of 0.8? So let's say you're in contact with the ball for 1.2 seconds, which is completely unrealistic, but I chose some numbers. 207.5 times 1.2 plus 2 times minus 44 over 2, we get 80.5. Why that's unrealistic? That's like 170 miles per hour. Baseballs go about 90 miles per hour, 100 and something if a pitcher hits it. I don't think they travel that fast off of that. But you can see here, reducing the time of impulse, you'll actually get a smaller change of momentum, okay? In this case, we reduced it so much, it continued traveling in the same direction, even though it had an impulse that slowed it down a little bit. It slowed it down to 12.9 from 44 meters per second. Here, by extending the impulse, we got a greater change of momentum. And so it had greater momentum as it left. And that's really it. Another great momentum problem, and I love this one. This is just talking about how we can't measure, is a car crash, okay? So this is my seatbelt question for everyone. And it's, why do you wear a seatbelt? How does a seatbelt save your life, okay? And we're gonna talk about it in terms of momentum. So let's imagine you're in a car and you're traveling at, I don't know, 40 meters per second. So you're doing like 90 miles an hour, okay? And you hit a solid wall, let's imagine. You hit a solid wall. And when you hit it, you immediately go to 0 meters per second, okay? And this impulse, let's say, lasts for 0.6 seconds. We want to know the average force on the crash test dummy, let's say, when they hit the wall. Now, we know F average times T is mv final minus mv initial. Let's say this mass is 1,600 kilograms. So the average force would be 1,600, the final is 0, the initial is 40 over 0.6. So negative 1,600 times 40 divided by 0.6 is 1,600 times 40 divided by 0.6 is 107,000 newtons. Incredibly bad, right? I mean, you're doing 80 miles per hour and you hit a solid wall and you stop. Usually you bounce off, something like that. But the average force on you would be insane. So you actually have two things in your car that are designed to save your life. You actually have a lot of things, and we're going to talk about a few of them. But in this scenario, we can actually come back and look at this. Now, you yourself, let's say you're the crash test dummy and you weigh 60 kilograms of that 1,600, okay? Which means that the average force on you is MA, or F average divided by M is equal to A. So your acceleration is this 170,000 divided by 60. Is about 1,800. Let me make sure that's right. 1,800 times 60. I think I messed that up. Yeah, there's 108. Yeah, okay. So you have about 1,800 meters per second squared acceleration. That is insane, right? If I further divide that into G's, so divide that by 9.8. 1,800 is about 184 G's. This is equivalent to 184 G's of acceleration. You're going to die, right? Your body is going to die. So what do you have in your car that will save your life? Well, first of all, you have a seatbelt, and a seatbelt we're not really going to talk about. Seatbelt keeps you in place. You also have an airbag. What an airbag does is it inflates and then rapidly deflates. So it inflates and then quickly deflates, so that as you hit it, you kind of sink into it and it deflates underneath you. We also have plastic cars, I'll call them. And we'll talk about these two things. So right now we're saying that if we go from 40 meters per second to 0 in 0.6 seconds, we feel 184 Gs on us, which is definitely a kick. 10 Gs will knock you out, knock you unconscious. 40 or 50 Gs and you're gone. So I'm sorry to be morbid on this. So that inflating and deflating, what that does is increases your delta T. Let's say it actually increases it by half. Okay, so instead of 0.6, now we're at 0.9 seconds with our airbag. Well, if we look at this and we increase it to 0.9, we get basically F average is equal to 1600 times minus 40 over 0.9. Okay, 1600 times 40, 1600 times 40 divided by 0.90. And now I'm at 71,000 newtons. And if I divide that by my 60 kilograms, so if I divide by 60, I'm at an acceleration of I'm at an acceleration of about 121 Gs. So I've reduced it from 180 to about 75%. Now, the other thing that your car does, I used to drive a 69 Valiant. I love that car. That car was made of steel, solid, unforgiving steel. That car could drive through a brick wall. Your car nowadays, I drive an Accord, a 2019 Accord. If I hit something, it comes apart like it's made of Legos. If you've ever dropped Legos, it blows apart. The reason why it does that is each of those little pieces is going to carry away momentum, so that essentially this makes the mass reduce. You carry away momentum with all those plastic pieces that go flying away. So when you get really mad and someone rear-ends your car on the freeway and you get mad because your car's wrecked, and yet you're standing there looking at it and there's pieces everywhere, be so happy those pieces carried away are mass. Let's say we can reduce the mass by 1/3 and we have our airbag. So now our mass is, let's reduce the mass by 1/4. So our mass goes to 1,200 kilograms. So now we have our F average is 1,200 times 40 divided by 0.9. So we're having our airbag and our mass. 1,200 times 40 divided by 0.9 is 4320 or 200 newtons. If I divide that by 60, divided by 60, and then I divide that by 9.8. That was weird. 720 divided by 9 is 73 Gs. Certainly not great, right? You're probably not going to survive that. But basically, by having a breakaway car and a airbag, we reduced the amount of acceleration your body felt, the average force your body felt being slowed down, by more than half. It's even more had we been doing a reasonable speed like 30 miles per hour. So we're only doing 15. This would be 15, and that would obviously reduce it to a third of this, about 20. So at about 30 miles an hour, you would probably survive a crash with an airbag and a seatbelt. It's really good. And these are just numbers I'm throwing out there. These aren't even the numbers that, really fit. But yeah, if you ever have someone try to tell you that an airbag is like soft, airbags aren't soft. What airbags are designed to do is not give you somewhere soft to land. What they're designed to do is to increase the amount of time of your impulse. And by increasing the amount of time, right? So if you look at this, our average force during an impulse is mv final minus mv initial over t, or our change in momentum over t. By increasing t, we decrease the force that occurred, the average force happening to us. That's really important, and it's really, really, really worth noting. Secondly, if we reduce our mass somehow by carrying away momentum, break away things. If you ever watch racing, Indy cars are designed to blow apart. Number one, because they're light, but number two, to save the driver. Reducing your mass will reduce your momentum. Yeah, if you've ever seen someone that ends up with like a Volkswagen logo on their head from the dash, from the steering wheel popping open when the airbag comes out, something for all of you that are here, if you don't know, if you've never been in an accident or never been by an accident when an airbag deployed, I used to work at Mercedes and Honda. I was a mechanic. When an airbag deploys, it's full of like dust, and that dust blows out because it essentially deflates immediately. It'll look like the car's full of smoke. So you might run over and think, oh my God, this car's on fire, I gotta get this person out. And they could have serious injuries. So just make sure if you see that the airbag went off, make sure the car's actually on fire. And so you're taking that risk of maybe hurting them by moving them. You're doing it with the best of intentions. You think the car's on fire, but the car's not actually on fire. So just make sure you know that, if you don't know that already, that airbags do blow a lot of dust around, which is weird. I don't know what they're filled with. It's like baby powder or what, but they're meant to save your life, not be a pillow for you to land on. So yeah, just keep that in mind. But you can see how they completely do save your life by changing the impulse. Impulse is cool. So there's more. I changed some of this time and seconds and stuff. But you can go through that example on your own if you want. And then we need to talk about, so we basically have collisions to talk about, and then the rocket equation. And collisions will definitely be on a quiz on Monday, or they'll be on your exam. I guarantee it. I want to make sure that you understand collisions as we start to talk about them. So collisions are what we call billiard ball or pool ball problems. In these problems, we always are like, oh yeah, it's this ball and another ball. So mass A and mass B. And mass B is usually at rest, and mass A usually has some velocity. What happens is mass A can hit it, and if they bounce off each other, we assume it's something called an elastic collision. And these are almost always these type of masses, one-dimensional elastic collisions. We'll talk about what that means. If after they hit, they stick together and travel off together, that is inelastic. And we'll talk about what that means. Usually these show up in all types of problems. So you'll have like, I don't know, maybe like a piece of putty falling and sticking. Oh, nice. Thanks, Cole. Anyway, yeah, so Cole said it's sodium azide. I don't know what azide is, but yeah, it's like a dust. Inelastic collisions, we generally talk about in any physical case. An elastic collision is usually set up like a pair of billiard balls. That's just the way it is. So, and we'll talk about what they each mean. In an elastic collision, so they come in, strikes, this one bounces off and this one heads up the other way, usually. In that type of collision, momentum is conserved and kinetic energy is conserved. Okay, that's kind of important. Do not try to write all this stuff down. At the end of this section on collisions, we will have 3 equations for you. 3 equations for you. You just need to know what the equations are, which cases they apply to. When objects stick, momentum is conserved. Momentum is always conserved. Kinetic energy is not conserved. So we'll talk about what that means and the difference between the two. Essentially, when objects stick together, they have to lose some energy from sticking together, and therefore their energy is going to be less, so they can't conserve energy when they stick together. But if they bounce off, they may. In real life, there's no such thing as a perfect inelastic or elastic. We're going to assume that there is. So we're talking about one mass and another mass. We'll call this one mass 1. We'll call this one mass 2. Mass 2 is always at rest initially. Now, before they hit, P initial, P final. And this is a one-dimensional elastic collision. So we have to write M1 B1 initial plus M2 B2 initial, and then M1 B1 final plus M2 B2 final. That is our conservation of momentum. If it's elastic or inelastic, it doesn't matter. These are the same. There's a small change for inelastic that we'll talk about, but for now, you don't even need to write this one down, but it's worth knowing. Secondly, the kinetic energy is the same. And I'm not going to write this, but you can write the total kinetic energy before and after is conserved in an elastic collision. So the sum of the kinetic energies is the same. Okay, so you always have to make sure that your signs are correct, meaning that before or initial, we have B, this is 1, this is 2, and we have B1 initial, and then say once they hit, 1 is moving off in the opposite direction, B1 final, and 2 is moving off in that way. This one would be negative. You have to make sure your signs are correct. We'll be doing one dimension, so just make sure you know your signs are correct. If I come back to these 2 equations here, this one and this one, by a long process of algebra, if you really want to try it, try adding this equation and this equation. So M1 V1 initial plus M2 V2 initial is equal to M1 V1 final plus M2 V2 final. By substituting, by realizing that, I don't know what the heck that just did. That was really annoying. By realizing this is 0, if we consider it, I'm going to kill those birds. Realizing those are 0 and doing a lot of algebra, you can actually come up with these 2 equations. And these are the 2 equations you need for elastic collisions. In an elastic collision, we are assuming that object 2 is at rest. So the second ball is at rest. Second object is at rest before the collision happens. After the collision, we're not sure what happens. We're gonna talk about that. Usually what you're given is you're given, say, mass 1 and mass 2 and V1 initial. And you've got to find V1 final and V2 final. Happily, you have two equations therefore. V1 final is equal to the difference in the two over the sum of the two times V1 initial. V2 final is equal to 2 times M1 over the sum of them times V1 initial. So they're both times the initial velocity. Now, there are actually a few cases that we're going to talk about here. But these are the equations you need to know. You need to understand there's no change in the kinetic energy in a one-dimensional, perfectly elastic collision, which isn't physically possible, but we're going to see. So let's look at our first case. What if M1 and M2 were equal? So if M1 and M2 are equal, basically what we're saying is these are both the same mass. And then afterwards, what happens? Okay. Well, M1 minus M2, if these are the same mass, V1 final is 0. It hits and it stays there. V2 final, if these are just, say, 1 kilogram, this would be 2 times 1 over 1 plus 1, which is 2. And you would just get that V2 final is identical to V1 initial. What that means is if they are the same mass, if both 1 and 2 are the same mass, in an elastic collision, they exchange momentum. Meaning V1 times M1 is equal to V2 times M2. And if 2 is initially at rest before the collision, 1 will be at rest after the collision. That's only if the masses are the same. So if you know that V2 final is equal to V1 initial, you know the only way that can be true is if they are the same mass. That is the only way. And that's a trick that sometimes happens. To be tricky, they'll be like, oh, well, V2 final is the same as V1 initial. What's the mass of mass 2? And it's like, it's the same as mass 1. It has to be. All right. The second type of collision is when M1 is much bigger than M2. I call this the bowling ball colliding with the marble. So if 1 is huge, massive, and 2 is very tiny, right? Then essentially what we can do is, coming back to here, we can ignore 2, right? If we ignore 2, look what happens. V1 final is equal to V1 initial. So in the big bowling ball hitting marble, afterwards, it's still trucking along like nothing happened, like it didn't even collide. V2 final is 2 M1 over M1, 2 times V1 initial. So now the marble's going away with double the velocity. And, you know, it has to be like a 10th, maybe a 20th of the mass, right? But essentially, if M1 is much, much, much bigger than M2, then it doesn't even really affect it. The final thing is what we call the tennis ball hitting the bowling ball, or the marble hitting the bowling ball. So now 1 is very small and 2 is very large. When that happens, if we come back to here, if now we can ignore M1, essentially, right? What we see is V1 is negative V1 initial. So this is the small thing hitting the large thing. And afterwards, it's going the opposite way, right? It hits and it goes flying the other way. Since M1 is very small, it does move some, but it's going to be very tiny, right? Since M1 is much, much smaller than M2. And if it's very, 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 very infinitesimally smaller than M2, essentially it's not going to move at all, right? So those are the 3 cases. You have when they're equal. If they're equal, V1 is at rest after the collision, and all the momentum shifts to object 2. If M2 is smaller than M1, then M2 has twice the velocity after the collision. And if object 1 is much smaller than object 2, it heads back the other way. and then you have anywhere in between. So those are not too bad. Essentially, you just use these equations right here. Just know these ones, and you're all good. Know these. And this is particularly important. No kinetic energy lost. Usually what we do is we'll ask something like, what is the change of kinetic energy? If you know it's elastic, you right away just say, hey, it's 0, it's elastic. But you could also prove it because you can find V1 final and V2 final, and then you can write MV1 initial squared over 2 plus M2 V2 initial squared over 2 is equal to M1 V1 final squared over 2 plus M2 V2 final squared over 2. You know this is 0, so the kinetic energy has to be distributed between them. It's not bad. In our inelastic, once they run into each other, they stick together, which means they become one object heading that way. Okay. Hang on one second. Sorry. I heard my door open. I was like, what the heck? Anyway, in a one-dimensional inelastic collision, they stick together. The two big changes are, you can write this as M1 V1 final and M2 V2 final, but V1 final is equal to V2 final. So they stick together. You technically only need this equation, which is nice, because essentially you're usually just finding V final. If they're initially at rest, that's 0. And so you get that M1 V1 initial over M1 plus M2 is V final. Not too bad, right? It's just an equation. The energy lost, since the difference, K, the initial kinetic energy minus the final kinetic energy, actually I should switch that. The change in kinetic energy is kinetic energy final minus kinetic energy initial. So this is the final kinetic energy. They're stuck together, have the same V final. So M1 plus M2, V final squared, minus the initial. And this will always be some negative number. It'll always be an amount lost. Why? They lose energy when they stick together. There's some energy lost to electromagnetic forces. There's some energy lost to friction, to heat, to whatever. But in an inelastic collision, they stick, they lose energy. And that's all you need to remember. So this is inelastic. Remember this, and remember that this is not equal. In fact, it's always lost. And remember, for elastic, V1 final is M1 minus M2 over M1 plus M2. V1 initial. V2 final is 2M1 over M1 plus M2. V1 initial. V2 at rest in both these cases usually. It doesn't have to be in this case, but usually in the elastic collision to use these, it has to be at rest. Now, there was something I was going to say and I don't remember now. I was like, oh, I'll put that back there and I'll bring it up in a second. But yeah, these aren't too bad. And once you do a couple of them, they're super easy. In multiple dimensions, you just handle it in multiple dimensions. So you'd have V1x final is M1 minus M2 over M1 plus M2 times Vx initial, and V1X initial, and V1Y final would be M1 minus M2 minus over M1 plus M2. V1Y initial, et cetera, et cetera, et cetera. You can just break them up. So you can do the change in kinetic energy, change in momentum in X, Y, and Z separately. There is one problem that I want to talk about, and then I want to talk about rockets. This problem comes up a lot. Now that we've used energy, this might actually help you kind of figure out energy and the change in momentum. So when police, like forensic detectives, want to figure out how fast a bullet travels, like the muzzle velocity of a gun, they will have a bullet, and we're going to call this MB for the bullet, traveling at some initial velocity. They fire it into usually a block of wood or rubber or something that's attached by a string to a rope. After it hits, we assume the bullet is buried in the ballistic pendulum. So we now have M of the bullet plus M of the block, right, is now this mass, and it has some V final, okay? And then it's going to swing on that rope some angle so that it achieves some height before it stops swinging up and starts to swing back, okay? So basically what the ballistic pendulum has is 3 steps. It has the initial, which I'll call 1. It has right after collision, which I'll call 2. And then it has max height, which is 3. Now, what we do is between 1 and 2, we use P initial is equal to P final in elastic collision. Okay, so we're going to use an inelastic collision to get V final. And then between 2 and 3, we're going to use energy to get H. And then we're going to work backwards. So let's talk about this. Imagine we have a block with a bullet in it and a block with a bullet in it, right? So it swings up to some height. This length is known. This angle may be known, okay? And we want H. Now, here, this will be L cosine of the angle, right? See that? If this is our length, this is L cosine of our angle. This whole thing is L. So our height is L minus L cos theta. That is what our H is. Our energy at A and our energy at B are equal. Energy at A, we're going to assume it has kinetic energy, mv final squared over 2 plus mgha. mv, let's call it A, vb squared over 2 plus mghb. Energy, conserved. All we do is write the 2 types of energy we have. We set them equal to each other. That's not equal, that's addition. Now, I'm going to assume that H at A is 0 and H at B is this L minus L cos theta. So this goes away. At maximum height, velocity is 0. So what I get is m VA squared over 2 is equal to mg HB, which is L times 1 minus cos theta. Okay, I can cancel these. So I get VA squared is 2GL 1 minus cos theta. That is my final velocity from energy. Next, I want my collision. Prior, the initial, M of the bullet, M of the block, V of the block is 0. After, exactly in the second before it begins to move, but they've collided, MB plus M of the block. And there is some V final. P initial, P final. M of the bullet, V initial of the bullet. this is all 0, is equal to m of the bullet plus m of the block, v final. Now, I can actually divide through by mb, m of the bullet, and then I have m of the bullet plus m of the block divided by m of the bullet, and then going back to this, VA is my V final. And so that is times the square root of 2G L 1 minus cos theta. This is a very cool problem. So let me write that in a new, V initial is equal to m of the bullet plus m of the block divided by m of the bullet, square root of 2g length of the string holding the block 1 minus cos theta. Cool problem because if you know how to do it, it's really fast. The energy part's not hard, it's just mv squared plus mgh at the bottom, at the top. It's an inelastic collision, so we just have m of the bullet times vb is equal to m of the bullet plus m of the block, v final, and you get this. But it's a really nice problem because you have to know energy and you have to know inelastic collisions. So if we put this stuff in to find the initial velocity, this is showing this stuff, assuming this was 0, where big MB is the block. So we get this, which we found. Using this, L is 1 minus cos theta for H final, and having some equation, or some of these, like the degrees are given to you in that problem in the slide before. You can easily find this. It's really nice. And this is one technique that they would use sometimes. They also will fire them, I think, into blocks of gel, and they somehow figure out how far it went through the gel, which is not something we're going to do. But this is an old school way of figuring out the muzzle velocity of a ballistic pendulum. So final thing, because I do want to get some homework, I want to talk about the homework before we leave, is one of my favorite things to talk about. And that is that back before World War II, okay, during World War II, us and the Russians, or I mean, us and Germany, developed rockets. A guy named Goddard was working on them here. The Germans were working on their V2 rockets. And Goddard wanted to create rockets that could fly in space. And there was a huge, huge, huge debate among supposedly very, very, very smart people who said that rockets couldn't fly in a vacuum, and that they wouldn't be able to fly in a vacuum because there was nothing for the rocket to push against. They said, oh, when rockets launch, they push their exhaust against the air, and it's a third law of air. It's the force of the air pushing back on the rocket. Well, that's not it at all. A rocket moves through something called conservation of momentum. The reason why we're going to study it, it's an example of what we call a mass differential problem. Now we know that P is mb, the momentum is mb, and we know that an external force is the change of time of the momentum. But what we haven't exactly established is the fact that since this is dm v dt, what if the velocity was constant, but the mass changed? How can mass change? If you've ever shaken up a soda bottle and launched it into the air, and it shot the soda out and went flying away, that is a differential mass problem. It's losing mass as it's accelerating. You could have the really old example that I don't know why they still use is coal cars. Cars full of coal, and the coal's falling over the side of the railroad car. And so it's falling out and the car's losing mass, but its velocity is staying the same. So it's got some stuff happening. Weirdly, that all can be applied to the rocket problem. A rocket in itself is basically just a long mass with fuel inside. So it has some fuel, and the fuel is lit on fire and it leaves. We're going to actually talk about this little bit of fuel leaving that we call DM, and we're going to call it negative. And we'll talk about that in a minute. But how do we solve this problem? Well, we solve this problem with momentum. It's a conservation of momentum equation. When a rocket is in space, it basically heats up some fuel. That gives that fuel a certain amount of velocity. So that little bit of fuel has some mass, DM, is leaving it. And it's going that way. And much like the wrench and the guy in the spacesuit, if that momentum is going that way, and we assume this is a closed, no external forces system, then the rocket has to be gaining momentum equal to it in the opposite direction by conservation of momentum. It's anyway, I'm sorry, they're barking. So it's pure conservation of momentum. It's a little bit tough to get through, but when we get to it at the end, it's a very easy equation. So this is just talking about my short history of rockets. So what we say is that initially the rocket, as it's traveling, has a momentum, the initial mass, fuel, rocket, times the initial velocity, which we're just going to call v. After a small time later, we know that the rocket is now traveling at v plus delta v, but there's also a little bit of fuel. So we actually have to account for this guy too. Now, if you remember the velocity addition, if this is some v exhaust speed, okay, and this is some little dm. Now dm is negative by, it has to be negative. It's actually a negative quantity, meaning that when we write m naught plus dm, this is actually a negative quantity in here, but we write it m plus dm. So this is m naught plus dm. They're still moving with that change of velocity. It's essentially like the rest frame issue. So it's got that momentum as it goes, minus the change of momentum, which is v minus v exhaust, whatever this exhaust speed is coming out. That might not make a lot of sense to you, but this is the equation. So this is the initial mass, v plus some very small change in the velocity, plus the mass that was leaving. So this is inherently negative. So this is actually less than m naught times v plus dv minus, or minus a minus, that amount of fuel leaving, v minus v exhaust. So this is the speed of the rocket, this is the speed of the exhaust, okay? From that, what we do is we write momentum initial equals momentum final. I don't believe your book goes into this much detail. It really should. It doesn't. It kind of gives you the final equation. But if we write the initial mass, which means m naught is rocket and fuel mass, the total initial. So, and then we start multiplying things. M naught v, m naught dv, vdm, dm dv, minus vdm, minus vex dm. A couple of things here that we have that we're going to be a little creative on. This is a very small mass times a very small velocity. Something very, very, very tiny times something very, very, very tiny is something really extraordinary tiny. So we say that's zero. This term and this term are positive and negative, they cancel. And we have this term and this term cancel. So what we're left with is 0 is equal to m naught dv plus vex dm. We're going to assume the velocity of the exhaust is constant. It's a constant amount. And we get this very nice equation. Now, we're not done. We're going to do a couple things to this. So I have m naught dv is equal to negative v exhaust dm. Divide by dt on both sides. Constant, constant. dv dt is acceleration. Minus vex, this right here is the amount of mass lost in a certain amount of time. We write that as R, and that is the mass loss rate in kilograms per second, okay? So we have this thrust, which is what we call this. The initial thrust is equal to the exhaust velocity times the mass loss rate, okay? It is a negative quantity. Although technically it's a positive quantity because dm is technically considered negative, blah, 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 blah. The thrust is negative VEXR, okay? That is our first equation. So the mass loss rate, R, is a constant. Assuming it's negative dm dt, we get this equation. So we get thrust is equal to VEX times R, where R is the mass loss rate. That's really cool. Initial thrust of a rocket is simply a number times a number that can be easily found. The harder part is how do we find the velocity of the rocket at any time? Coming back to m naught v dv is equal to minus vex dm. If I write it like this, so dm over m naught, take the integral, leaving the negative vex outside. Let this go from v initial to v final. This go from m initial to m final, okay? This becomes v final minus v initial. It's just the integral of dv. This is the integral of dm over m naught, okay? From m initial to m final. Now, actually, and I shouldn't write it m naught. I thought I was being weird, but it's actually not m naught, it's m over m. The integral of 1 over m is ln. So this is minus vex ln of m final minus m initial, right? You can write it. Let's talk about that for a minute. So we have v final minus v initial is minus vex ln of m final minus ln of m initial, okay? Now, if you don't remember, and it's okay if you don't remember, although I would review them, the rules on ln's. So when they're minus, this is ln of m final over m initial, right? But with the negative, they actually switch. So v final is equal to v initial plus vex ln of m initial over m final. Okay. So coming back to this, we can find m final given a time and a mass loss rate, right? So R is kilograms per second. So the mass final is mass initial minus R times time, okay? So you can subtract the mass lost in some time from the initial mass, find the mass final. And if you know that it starts, say, at rest, you can find the final velocity of a rocket, right? So this equation right here and this equation, m final is equal to m initial minus RT, and this equation, thrust is equal to R VEX. These three equations are really all you need. maybe you need that thrust is MA. I don't know. All right, so let's look at this. A rocket has a mass of 4,000 kilograms plus 15,000 kilograms of fuel. It burns 50 kilograms a second with an exhaust velocity of 230 meters per second. What is the thrust and acceleration of the rocket? Okay, let's talk about what these are. M initial is going to be both of those, so 19,000 kilograms. R is our mass loss rate, kilograms per second, and VEX is 230, the velocity exhaust. The thrust is minus VEX, or positive VEX times R, which is 230. I'll let you do that yourself in newtons. All right, what is the acceleration? Well, this is MA is V exhaust over R. So A is simply V exhaust over R divided by M naught, which is 50 to 30 divided by 19,000. That much is okay. After 100 seconds, how much mass is left? M initial minus RT is 19,000 minus 50 times 100, which is 5,000, so 14,000 kilograms. What is the velocity of the rocket at 100 seconds if it started from rest? V final was VEX ln M initial over M final, which is 230 ln of 19,000 divided by 14,000. I can actually do that one on my calculator just for the heck of it. 230 times, where's my ln? My eyes are horrible. ln of 19,000 divided by 14,000 is about 70.24 meters per second. Not super fast, right? 140 miles per hour. 160 or 70 miles per hour. Not hard. They're all plug and chug. It's really just identifying your numbers, right? Yeah, these problems aren't hard. And I gave you one on the homework. So basically, what we've had today, and I'm going to go over some homework in a second, but what we've had today is we had the center of mass, which was, we just do M1 x1 plus M2 x2 plus blah, 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 divided by M total, right? And we had some momentum stuff. We had F times delta T is M V final minus MV initial. And we had, for a elastic, we had V1 final is M1 minus M2 over M1 plus M2, V1 initial, V2 final, 2M1 over M1 plus M2, V1 initial, inelastic, and delta KE is 0. Inelastic was M1, V1 initial is M1 plus M2, V final, and KE final minus KE initial does not equal 0. Stick together. We have thrust is VEX R for a rocket. A is VEX R over M naught. V final is V initial plus VEX ln M initial over M final. Maybe ballistic pendulum, but you can see a lot of this is just, oh, is this an impulse problem? So I just plug this stuff in. Is it elastic? Did they hit and bounce off? Is it inelastic? Did they hit and stick together? Maybe review the ballistic pendulum one. That one's a pretty good one. But as you can see, we're not going to have like a integral or anything to find the center mass. You're not going to probably have to find the center mass on your exam I'm not going to do that to you. However, I do want you to know how to do it because it comes up again when we start talking about torque. In fact, we need to find the moments of inertia, and they have a lot to do with center of mass. So I do want you to understand center of mass, even though you won't have any test questions on it. No inelastic and elastic. Make sure you know those two. You could have a rocket problem, probably won't, but I guarantee you, you will have some kind of impulse, momentum, elastic, and elastic type problem. So chapter 9 homework, as you go through this, and this is due the day after our exam. So you have 2 weeks to do it. To go through it, take your time. There won't be another homework assignment until after the exam. So take your time on this, but we have a couple of center of mass on this first one. Now, you have to note that this L, this beam right here, which is 11 centimeters and has a mass of 54, is along y is 0. Okay, so what do you know? You know right away that the center of mass is going to be at the halfway point of this L. But where is it in the y direction? You're going to have to use that y center of mass is equal to right y, left y, and center y, horizontal y, which is also 0. So you just need to figure out where the y is when you divide by the mass. The x coordinate is going to be in the center. You can see that from symmetry. Okay, that one's not too bad. This one is a pain. And so for those of you who are here or watching this at home, this is super helpful. Now, you have the length and you have the distance, right? So this is a ammonia, nitrogen, hydrogen molecule. They gave you the atomic mass ratio for nitrogen to hydrogen. There are 3 hydrogens and 1 nitrogen. The total mass of this is 13.9 hydrogen plus 1 hydrogen plus 1 hydrogen plus 1 hydrogen, which is 16.9 hydrogen masses. That is the total mass, right? That's what this means. The distance L, okay, is given, and D is given, and you need to find the height, because basically you know that it's going to be at the center. So if they're saying that this is at the origin, then you know that it's where the nitrogen, the center mass, is along the y-axis of the nitrogen. However, how high up or down it is, the y coordinate, you're going to have to find. And for that, you're going to have to find this height and then divide by the mass over the total mass, right? It's not bad, but just remember, you need to find that height. You have L, you have D. L squared is equal to D squared plus H squared. So H squared is equal to L squared minus D squared, if that helps. Square root of L squared minus D squared, trigonometry. All right, this one's really cool, okay? This problem I would actually do in lecture if I didn't give it to you for homework. But this thing is shot with an initial velocity of 20 meters per second at an angle of 55. You should know how to find the velocity in the x direction from that, okay? So if v initial is equal to v initial and y, v initial in x, I mean, is 20 times cosine of 55, right? So we know the velocity in x from projectile motion going all the way back to whatever that was, chapter 4. V naught cosine of 55. When it's at the top, max height, it only has velocity in the x, right? It only has v of x. So this thing, before it breaks apart, it has m naught, v naught in the x, where v naught of the x is v naught cos of the angle. Then it's going to break into 2 chunks, one which has V initial in the X and V initial in the Y, or just Vx and Vy, are both 0, and one which has Vx is unknown. So assuming that the terrain is level and that air drag is negligible. Okay, so Vx is if we have the initial velocity is m1 plus m2 v naught cos theta, and then afterwards we only have m2 because m1 fell straight down, v final. They're both equal mass, so that means that this is 2m and this is m. So v final is 2 v naught cos theta, which means it's double the speed, which means it lands twice as far away. So what I could do is find the time total, because y initial minus y final is equal to v naught t minus gt squared over 2. Remember, if y initial and y final are the same, that's 0. That means t is equal to 2 times v naught over g, but this is v naught of y. 2 v naught sine theta over g is our time. And x final is v of x times t. So x final 1 is v naught cos theta times t to the half. And x final 2 is 2 v naught cos theta times t to the half. So basically, x final is v naught cos theta times t to the 1 plus 1/2, or 3/2. If you didn't follow all that, go through it slowly, go back to projectile motion. But the cool thing is when the explosion happens, one of the particles has no momentum. Because there are no external forces, the one that keeps going, gets double the momentum. At the top of the motion, you know that there is no y velocity, so all of the motion is in x, and because it gets all of the momentum, it gets double the momentum, because each mass is half of the mass. It's a fun problem if you like doing these problems. Okay, and Taekwondo, which is a type of fighting martial arts, a hand is slammed down on a target at a speed of 14 meters per second and stopped in 6 milliseconds, 6 times 10 to the minus 3. Assume during the impact, the hand is independent of the arm and has a mass of 0.6. What are the magnitudes of the impulse and the average force? So the impulse is just the change in momentum. We're assuming v final is 0. So mv final is 0 minus mv initial. But if we assume v initial is negative, then we get 14 times 0.6. That's just our momentum, our initial momentum. Our average force is that initial momentum divided by 6 milliseconds, 6 times 10 to the minus 3. It's not too bad. Plug and check, really. A 1 kilogram ball drops vertically to the floor, hits with a speed of 26, rebounds with an initial speed of 7.7. So we know dropping down, let's call that negative. What impulse acts on the ball? 1 kilogram. As it's dropping, I'm assuming that's negative. So V initial is 26, V final is positive 7.7. So MV final minus MV initial, 1 times 77 minus 1 times 26, or 1 times a minus 26. All right, so that ends up being a nice big number, 26 plus 7.7. If the ball is in contact at point for 0.0088 seconds, what is the magnitude of the average force? Again, divide that by the time. They're pretty simple. You should be able to knock this out pretty fast. Completely inelastic, what does that mean? They stick. Two balls move directly toward each other along a vertical axis. Just before collision, one is moving up, the other is moving down. How high do they rise? Okay, neglecting air. So you need to find the velocity right after collision. M1 times V1 is 3.3 positive 22 plus M2 1.7 times V2, which is negative 13. So you have a positive number and a negative number. And then you can use projectile motion to see how high they go up. Remembering that V final is 0, V initial, V final squared minus V initial squared is equal to minus 2G, Y final minus Y initial. Isn't too hard. So this is an elastic collision. M1 V1 plus M2 V2 is equal to M1 plus M2 times V final. Once you do that, it's just V final squared minus V initial squared is minus 2G, H final minus H initial. All right. So it's a little bit of projectile free fall stuff. Here, this is like the ballistic pendulum. It's going to drop from a height, hit this steel ball. It's an elastic collision. So we're going to find the ball, mv squared over 2, 2gh. We're told the cord is 51 centimeters long. So that's an initial height of 51 centimeters, 0.51 meters. We know the mass. We can find the speed. Once we know the speed of the ball right before it hits, we can find the speed of the block and the speed of the ball after collision. It's inelastic, right? The block is at rest. So use V1 final is M1 minus M2 over M1 plus M2 times V1 initial, which you found from square root of 2GH. The block is 2M1 divided by M1 plus M2 times V1 initial. So V1 initial is going to be square root of 2G H initial.
I put this in the freezer.
Yeah. Is your mom here?
No, she called me and told me that she had groceries delivered.
Oh, yeah, put that in the freezer. And then this is initially at rest. So it's not too bad. It's elastic with a little bit of energy. Here's another one, elastic collision, mass of 4.6, and continues to move in the original direction, but at 1/8. So you know what V1 final is. It's an eighth of V1 initial. Knowing that, you can get rid of the V1 initial. Basically, think about it like this. You have V1 final is 1/8 of V1 initial is equal to M1 minus M2 over M1 plus M2, V1 initial. So you can cancel those. And then you can find M1 plus M2 is equal to M1 minus M2 times 8, or 8M1 minus M1 is equal to 8M2 plus M2. So 7M1 is 9M2. And once you find that, you can figure out what the mass of the other body is. What is the speed of the two body center of mass if the initial speed of the 4.6 kilogram body was 7.4? Now, the initial momentum and the final momentum of the center of mass have to stay the same. So the initial momentum was 4.6 times 8 times whatever that initial speed. You're going to need to find the initial speed. Oh, yeah, it gives you the initial speed. I'm sorry. So the initial momentum was 4.6 times 7.4. The final momentum of the center of mass needs to be the same as that. Okay. So the center of mass would be both masses divided by this. So if I know both of these, I would get 3.58 plus that is 8.18. So 4.6 divided by 8.18 times 7.4. Yep. So basically, by conservation of momentum, center of mass, right, means the total mass, the sum of both masses, times some velocity has to be equal to the initial momentum of the 4.6 block which in this case 4.6 times 7.4 has to be equal to the sum of the two masses, whatever you find. If I add 3.58 and 4.6 times some V final, and that V final is the speed of the center of mass. Hopefully that makes sense to you. The initial momentum and the momentum of the center of mass after collision have to be the same. Quickly, rocket in deep space is initially at rest, has a mass, an initial mass of that, and fuel. It's fired for 270 seconds. It gives you the weight, the R, 300 kilograms per second. It gives you the exhaust speed in kilometers per second. So make sure you turn this to meters, 3,000 meters per second. What is the rocket's thrust? After 270, what are its mass and what is the speed of the rocket? I've already done that one. Same way that I did that problem. Particle 1 has a mass of 261 grams, turn that to kilograms. They give you the speed. One-dimensional collision with particle 2, mass 323. What is the magnitude of the impulse if the collision is elastic or completely inelastic? Now, what is the magnitude of the impulse? F times t, okay, is equal to the impulse, which is equal to the change in momentum, right? So what they want to know sorry, my brain just decided to check out on me for a minute. So the impulse, what you need to do if it's elastic, you need to find V2 final and V1 final. Oh, I'm sorry. I'm just being dumb because I'm thinking if it's completely elastic or inelastic, the momentum should be the same. And I'm trying to figure out why they're getting something different. Because we use the fact that P initial is equal to P final, and they should be the same. So I'm a little confused. What they want you to do on this is that, but oh, I get what they're saying. I'm sorry. Yeah, I'm losing my brain a little bit because I'm thinking, well, the whole system, P initial and P final. So let me draw this for you. So normally we use that P initial is P final for elastic or inelastic. What they want though is they only want it for M1. So normally we would say M1 V1 plus M2 V2 initial has to be equal to V1 final plus M2 V2 final in elastic or inelastic collision. The only difference is if it's inelastic, this is the same, right? And M1 V1 initial plus M2 V2 initial. Now, these are both that, but they're still equal. So I'm like, well, J is the change of momentum, so it should be 0. What they want is the change of momentum for M1. So they want M1 V1 final minus M1 V1 initial for each of these, in each of the cases, okay? So in inelastic, V1 final, in elastic, V1 final is M1 minus M2 over M1 plus M2, V1 initial, and in this is elastic, V1 final is M1 V1 initial divided by M1 plus M2. So it just wants it for particle 1, not both of them. So the answer is not 0. And that's it. That's question 10. You have 2 weeks to do these. If you didn't see, I did open the Lab 8 to a week from Sunday or a week from yesterday. Otherwise, we're done. I'm gonna go unless anyone has any quick questions for me. Yeah, that's fine. Once everyone gets gone, Jennifer, we can meet. So, thanks, everybody. I need to meet with Jennifer unless you have a quick question for me.
Bye, Professor. Thank you.
Bye, Sam.
Professor, I do have a quick question.
What's up, Lucas?
I was wondering if this cup would work for the experiment.
Yeah, that should work. What I did was I took like a really small pen and just cut a little hole in it so that I could run some thread through it.
Thread? All right.
Yeah, because you're gonna need to weigh it. I don't have my cup with me, but I ran a piece of thread, it made a little hole right at the lip, and I tied dental floss through that little hole so that I could just hang it on the bottom of the iLab eyeball. Does that make
Okay.
sense?
Yeah.
Yeah, so I had to find something sharp enough that I could kind of poke a hole without breaking the cup.
Okay. Got it.
All right. Hey, Sammy, I need to talk to Jennifer. You still here, Sammy?
Oh, sorry, I was on mute. I was trying to say bye.
Oh, bye.
Oh, one last quick question.
Sure.
For the eraser experiment, when you need a square, does it
Uh-huh.
have to be new or can
No, just make sure that it doesn't float.
it doesn't float? Okay, got it.
Yeah, if it floats, it won't give you great numbers.
Okay, so the wrist can be used. Got it. Cool,
Yeah.
thank you.
Hey, Jennifer. I know we've been playing email tag.
I know. Thank you for meeting with me. I had a question regarding I think it was, I know it's so far back. It's a question regarding homework 4 and 5. I think I had sent an email about it. But before we dive into the email, I just first of all, I want to apologize for earlier interrupting at the beginning of the lecture with my call.
Oh, I don't care. It happens.
Yeah, I have a situation at work in which it looks like they're dissolving my department where I work, or it's looking like that. So I'm maybe out of a job.
Oh, bummer.
Yeah, so and I'm not from California, so there's a chance that I may have to move back.
Uh-huh.
And it might be after the drop day. So if I don't show up for like the final exam or something, it's because of that.
Yeah, so what happens with that, Jennifer, is you get what's called a WF. A WF means that you didn't finish the course. It can have a small negative thing. I don't know for sure how negative it impacts your financial aid. So
I don't have any financial aid, so I'm not worried about that.
Okay, yeah, it's just it's basically saying, hey, I didn't fail them. I didn't have enough time with them to give them a grade. And I tend to do that when people just end up not showing up instead of dropping them.
Yeah, I mean, I don't know if there could be a scenario in which I could take the exam through Proctorio.
Jennifer, if something happens and you want to make sure and try and get your grade in, cool, do it. Just let me know and I'll send you an exam or something, okay?
Okay, I just didn't want to ask, because that's unfair.
No, I understand. And I mean, honestly, a lot of students are doing a lot of things, and that's why they're at community college, because they're trying to fit it in with everything else that's going on in life. And I understand that totally. I was there at one point. As far as the homework, what I would do is, I know you missed a bunch of homework. So the only thing I'm worried about is this set. So 7, 8, 9, or 7, 8, 14. So this one that's due tomorrow, let me actually make that due on the 23rd. Jump off that. So on those old homeworks, don't worry about them right now, Jennifer. We'll worry about that at the end.
Okay.
Don't think like I'm gonna be like, oh, well, you didn't do your homework and that's why I gave you a C-. I'm not gonna do that to you.
Okay. I mean, if there's a possibility in which I can get a chance to do them, it's not that I didn't do them because I didn't want to.
Yeah, if you want to, the thing that I'm thinking with it though is that stuff is not, we're not going to really cover it anymore. So I think you would be better served to just make sure you've got 7, 8, and 9 down for the
Okay.
next exam. Just worry about that, and then we'll talk about like that stuff when it comes time for grades. What I care most about is that you get your money's worth out of the class, that you feel that you've learned at least a decent amount.
I've already learned so much more compared to the other class that I took. I took one in the spring and it was very hard for me to follow because of the, like, what you're saying automatically makes sense versus the other person who was teaching it. Like, and it has nothing to do with the person. Some people have different learning styles.
Yeah, and I know that.
And so, yeah, so I'm already getting much more than I did in the other class.
Cool. Yeah, and that what's important to me is eventually somewhere you may have to take another physics class. And I
Yeah.
don't want you to fail it because I did a horrible job with you. Grade wise, I'm pretty easygoing. If you've done the work I've asked of you and we've talked about work that you maybe missed, I tend to be easy to talk about grades and figure out what you need and what you feel like you earned and what I'm comfortable giving you and all that. And I promise I won't turn into a total jerk, or a, you know, you'll be happy at the end of it if you get all the work in, and just let me know what's going on with having to possibly move, and we'll figure that out together, Jennifer.
Yeah, hopefully that doesn't happen. Because my boss is one of those like fancy grad kind of people who created their own department and then figured out they're not interested anymore, so they want to leave.
That's horrible.
And they're like sort of saying that it's going to be hard to backfill the people in our department because we're so small, and second of all, because we're a new service that it's like nobody has this, so it's like, where can we put you?
Yeah, I know how that goes. Just hang in there, and for now I just want you to concentrate on these 3 homeworks so that you're okay for the exam.
Okay.
On Wednesday after lab, I'm going to post probably 2 review exams, just like last time, for you guys. So you'll have hopefully 2 weekends to go through that material too. And we can talk about it. Maybe what I'll do is I'll try to put together, since this weekend's like a 4-day weekend, we have Veterans Day, maybe next Friday, I'll try to put together a little bit more review time for anybody who wants it.
Because the exam is not next week, right? It's on the 20th.
No. It's
Okay.
2 weeks from today.
I was worried that maybe I lost track.
No, I know. I feel like I've lost weeks here
Okay,
and there.
because all right.
I swear I've looked at things in my other class and I'm like, yeah, we're doing this today. And then I'm like, oh my God, we're not.
That's for a different class. Yeah.
We're like a week off. And I'm like, what the heck am wrong with my brain?
Yeah.
Yeah, but just concentrate on getting these homeworks, these last 3, and then the review that I post, or the practice exams I post on Wednesday, so that you're
Yeah,
okay.
'cause I think I entered class when we were doing 4 and 5, right? Closing.
Yeah, somewhere around there. Yeah.
Yeah. Okay, and then the other thing that I wanted to mention is that I used your data for lab 7 because I was sick over the weekend. And I don't have a lab partner, so I sort of used your data.
Yeah, and I understand that. I mean, sometimes people just don't have the material, or they try it and it doesn't work right. And I would rather you kind of have decent data.
And I was having a hard time finding a ramp that was steady.
Yeah.
It was.
I stole a
Yeah, it looks like a
Bookshelf.
bookshelf.
I stole a bookshelf off my son's bookshelf.
Yeah, that's what it looked like.
That's what I did. I was like, oh, hey, that's flat and hard. But if you have like a cookie sheet, that would work.
Oh, okay, I didn't think about that.
It just has to be something kind of solid and short, but if you want to use my data, that's fine.
Yeah. Okay. And then I guess I think I did this right, but I sent in, and I don't know how I can send this to you, but I just can't seem to get the right numbers. It was for like homework. Well, would you like for me to ask this question later? It's homework 5 and 4 and 4 and
Do
5.
you know which one it is?
It was
Homework 4?
it was about it's the one with friction, like the incline math.
Yeah. So that one is not chapter 4. That is chapter 6.
We get like 1.44 kilometers per hour or slash height, and then we have 18 meters, and then you have to use that formula A equals V square.
I don't have anything for you on 6.
Yeah, because I think I had asked for help and we were gonna meet on Monday, but then it didn't happen.
Yeah, that sounds like me, and I'm so sorry. I don't mean to laugh about that.
No, it's okay.
You know, if you want me to, I'll open that. Oh, don't do that, James. Don't do that. Don't do that. Sorry, I'm talking to myself. So homework 6, if I add, and
Are we sure it's homework 6? I could have sworn it was 4 and 5.
I don't have anything for you on homework 6. So if you want, I'm just opening it up for you.
Okay, thank you.
If you're on your laptop right now, go in and make sure that you can open it. Because sometimes it does this stupid thing with a date that I have to change.
Okay.
It's really annoying. I hate Wyland.
Yeah, well, it's way better than WebAssign. I'll say that.
Yeah, but the problem is that they like change it every semester and we don't get like told what the changes. Like we're told the
Oh,
big
I see.
ones. And then I'm like, wait, oh, if I do that now, it does this. And it's like, oh God, that's annoying.
Oh, I see.
There's
Yeah,
a date that's internal to Wiley, and then there's a date on Canvas. And sometimes they don't jive, and I get students saying, hey, it locked me out. And I'm like, it shouldn't, the dates are fine. And then I'll change the date and they're like, yeah, it's open now. I'm like, okay.
yeah, like for example, yesterday's homework, it said that it was due on Sunday, but it was graded on Friday, so I couldn't work on
Yeah,
it.
you told me that, and I'm like, I don't understand that, because even the date in Wiley, I think that was the one I just changed, right?
Yeah, the due date, yeah.
But if you go in, if I go in, so this is 7 and 8. If I go in and open it, and I go to options, I can hit edit, and it takes me into the stupid assignment builder. And then I go to assignment settings, and it says today by 11:15, cancel. And then if I change that to now 23 and hit save, it should be okay for you guys, I hope. But I don't know. I'm not sure.
What
See, it
happened?
says you set a due date in Wiley and in your LMS, make sure they match. I think they match. It said the 23rd and
Like for example, Canvas will say
23rd.
that it's due on Sunday, and I'll go in there and it'll be graded. Like it'll be graded.
Yeah, I don't know what that's
Like
doing.
Canvas and Wiley are not like connected.
Yeah, and they're supposed to be. So maybe I need to not hit that date at all in Wiley, but I don't know. I'll figure it out.
Yeah, so I just resent the email. I don't know if you received it for the one where the problem is.
Hang on a sec. Cindy, I don't have anything from you. Hang on. Oh, I do right there. Okay, so, wow, that goes back a bit. I had a question regarding section 4.5. What did that mean?
You
Section-
know, it was fresh in my mind then because I knew exactly what problems. So, but now that I'm looking at it, I also have questions about my question. But
What does that mean?
like I know it's problem number 2.
So here's the thing though. If it's 4, and you can still see my screen, right?
Yes.
Okay, so there's this one, which hopefully will eventually load. And so this, you stopped on,
Yeah. Is that the problem? Can we click on it?
this problem.
Oh yeah, that's the problem. Yes.
Okay, so with this problem, I don't know if you can do a screen grab of that.
A screenshot.
Yeah,
Yeah, I'll take a screenshot because I was setting it up with.
or even just take a picture with your phone.
Okay.
But yeah, that's basically the setup. And just to save me the time of having to
Okay.
edit all out. It's not too hard. I think it's pretty self-explanatory.
Okay. Yeah, it looks like I was not using the right formula.
So this is just the y final minus y initial is v of y, t minus g to the half t squared. And then this is just making sure you find the right speeds. It's actually not too bad if you follow it, but
Yeah, but I was just getting the wrong values. Like I kept putting them in there and changing the numbers, and it wasn't like it
yeah,
wasn't-
and these are supposed to be. So what was A was the height? Height of 25, yeah, I don't know.
So the way that I set it up, it was incorrect, it seems.
Maybe.
Tried to find the mass, and I got like 1427.1 kilograms for the mass.
For this, you tried to find the mass?
No, I was trying to find the mass and trying to put it into that formula.
I'm sorry, I think we're looking at the wrong, there's no mass in these formulas. Are we looking at different questions?
Can we go up? I want to see if I'm looking at the right one.
Oh, I'm sorry, did you want that question?
No, I'm trying to figure out where. I don't see, well, maybe yours has different numbers. I don't see.
Mine does have different numbers, but there's no mass in this problem.
Yeah, maybe that's a
Projectile
different.
motion has no mass.
Oh boy, okay, maybe it's a different, it's okay. Can I look at these problems even though they're graded on?
I don't know if you can or not. Can you?
I don't think so, but is there like similar problems that I can look at? So just.
Yeah,
so I know
so
what I am.
here's if you go into the Wiley book,
If you, okay,
okay, there is in the course-wide references, there are student solutions for the problems at the end. So in like chapter 4, let's say, if you go to chapter 4 of the book, at the very end of the chapter, and I don't think they're by themselves, but let's go to here. Come on, open it. Why do you take so long to load? If you go to the very end of the chapters,
there's questions.
Oh, come on. So there's questions and then there's problems. Oh, that's not what I was looking for. So come on, get to it. So we have these problems, right? Any of the problems that say SSM are in, I don't know what ILW is, but are in the student solution manual for chapter 4. So like
Okay.
4.5 is problem number 5 in chapter 4. And so you can go to these and try them, and then you can go through the student solution manual, and it gives a pretty nice, like, think, express, analyze, you know, solve, learn, blah, blah, blah. So they do a decent job with some of them. I sometimes will assign them as actual homework, just so that you can go through and check yourself while you're doing your homework. But yeah, just if you do go through the if you just go through the problems at the end of the chapter, there's also additional sample problems. This is like whatchamacallit, like little demonstrations. This is like Khan Academy style things, so you can watch them
Okay.
on different things. They're all here. Like for instance, we're doing chapter 9. It'll give like impulse and average. I'm not going to click on it, but I don't really like the guy's voice.
Here, I'm going to talk about the impulse and the average force.
She sounds
of a
like
collision.
the definition of like nerdy science guy, which is weird, but they're like Khan Academy, and if you know
I
you
see.
need it, you can spend 10 minutes watching it and
Okay.
see if it makes sense to you. Yeah.
But will doing all of this help me for your exams? Because I don't want to spend time learning other.
Yeah, that's I would really concentrate on reviewing my exam, because I kind of write my exams a certain way.
Yeah.
I try to incorporate all the things that they talk about, like, you know, what are the variables and what are the equations, and okay, now that we know what we've got, solve it, you know. So I don't know. It really depends on what you like to do.
Well, I want to
all
pass.
of the
So
homework-
I'll do what I need to pass.
Right, yeah. So like all of these though, and I shouldn't say this because this is really bad, but you
The
know,
problems are irrelevant.
all of these, if I copy and I go to Google and I paste, you know, we know that all of these they're all in like Chegg or they're online somewhere.
Yeah, I got rid of Chegg because I was studying I used Chegg as like an example on how to solve problems, not like to cheat like other students. And
Well,
I was using it to study, and one of the professors saw that there were similarities in the way that I solved it, and he said that it looked like I was cheating.
Yeah, and some professor can get like that. I can't do anything about that. So I just say, hey, you guys want to do your homework, you want to look it up on Chegg, go ahead. You're probably not going to learn from it.
Anything,
You might
right?
learn, but you're not going to learn.
Yeah, I feel like last semester it was like cheater, Nazi, boot camp everywhere, because everyone was like, looks like you cheated here, looks like you cheated there. And there was like so many lists on like, you better not do this or you'll be deemed cheating, you better not do that. And it was pretty bad. Like last year, like you weren't even allowed to think on your own, because if that was not on the syllabus, or like if you had a solution that was different than the way you were taught in class, that was cheating.
Yeah, and I don't know. I've only had a couple cases of people that I was pretty sure were cheating. And in general, what's sad is the cheaters, it usually doesn't help. Like, it's not like they're getting straight A's. They're barely scraping by it. And so what I try to do is I try to write tests that are more like demonstrate that you know what the heck you're doing, where you can't just write like copy what people are doing. And it's pretty obvious to me when someone doesn't know what they're doing. But yeah, there has been a huge problem. There's always, everywhere I've ever been, every university I've been at, cheating's always a problem. And
Yeah, it's been a problem for a long time. It's not new.
No, and-
Everyone knows those students who graduated because they're professional cheaters. Like,
Well, and
everybody-
you know, they're going to be in a world of hurt. when
yeah.
you get to,
I mean, I knew people who were cheating from high school and they were going into colleges that they shouldn't have been going to, and they graduated from those colleges off of like cheating.
yeah, no, there used to be this story about, I think it was USC. Like, if you had a Scantron test at USC, you could buy a pencil that had all the Scantron answers on it at the bookstore.
God.
Like, wow, that's pretty crappy. And so it's like, you can fight it. I personally, when we're in meetings with other faculty and the other faculty are whining about cheaters, I'm like, well, wait, what are you doing on your test? How much effort are you putting into your test? Because if you're making a test, like 3 different tests, and you're just rotating every year, and then you're mad because someone put it online, it's like, well, you deserve that. You need to like at least keep your test
Yeah.
fresh and write something relevant. Because I teach different stuff. I emphasize different things every time I teach. And I try to make sure that my tests emphasize, you know, you
Well,
do
yeah.
run the problem of there are only so many problems. And it's
Yeah.
like, you know, I can't write too difficult, but then I'm like, wow, that's a boring, easy question. But then I realize, oh, you guys don't know it though. So, yeah, it's fine. So I would just concentrate on the review when it comes out.
All right.
Wednesday.
Well, I'll go ahead and work on the solution. I took a screenshot of it, so I'll take a look at it. And like I
Okay.
said, if I do have to move or if something happens and
Let
it
me know.
disrupts my life, I'll let you know, because I don't want to fail and I don't want to excuse W or an F or whatever.
Yeah. Well, we'll figure it out, Jennifer.
Okay, thank you so much.
All right. Have a good one.